Good morning, everyone. Congratulations to those that made it on time. It's very reduced audience. I hope that we will be more soon. But it's my pleasure actually to welcome Nadia Blagorodnova with the invited talk on From Gaia Science Alerts to the next discovery machine. So the stage is yours.
Hello, good morning. So yes, I would love to present you like a new discovery machine. This is great to be here because I was a PhD student with the Gaia Science Alerts group with Gaia was starting. So I would make talks about how great Gaia would be to discover things. And many people would be a bit hesitant, but then it became a discovery machine. So I'm very pleased to actually present you the next mission that we are starting, which hopefully will also become a great success. So just to clarify things, because many of you were asking me, oh, you're from Barcelona, but is that the Autónoma or the other thing? So this is a bit the situation that we have right now in Catalonia. So there is the Barcelona city, which has the Polytechnic University, and then has the University of Barcelona, where I am now. Then there is a bit off, kind of 30 kilometers in, there is the Autónoma, which also has this Institute of Cosmic Sciences, ICE, and CSIC. So this is a research institute, but also the Autónoma University. And a bit south in Castelldefels, there is the headquarters of the Catalan Institute for Cosmic Sciences, but also another campus of the Polytechnic University. So there's like white dwarf people doing science here, and the university that's time domain and Gaia people, and here there's also like a supernova group. So this is a kind of a landscape. We are more or less together, but it's different institutions. But the main point is like we are part of this IEC, which is the kind of the Catalan umbrella for research institutes related to space. So from the Barcelona team, we have been contributing to alerts with some of our facilities. So the oldest facility is this one, is Joan Huró, is a 0.8 meter imager mostly. It has a spectrograph, but it's only for very bright sources. And then very recently, we have commissioned yet kind of another telescope, It's 40 centimeters, and same as this one, it's 50. It's all kind of broadband photometry. So it's mostly for like space debris, some exoplanet transits, and it's becoming available to use for the community starting from next year. So there is a growing number of telescopes, and what I'm most excited about is actually like a future project of a 2-meter telescope with a spectrograph. So we really are looking forward to this. The budget has been approved. We are just waiting for the money to kind of stream into the offices, of the team to start building things and making contracts. But this is happening. So as soon as everything is formalized, I mean, bureaucracy in Spain can be slow. Everything will be constructed fairly soon because it's mostly off-the-shelf kind of components and so on. The only thing is the spectrograph. We are still kind of ultimating the final design for this. But yeah, we hope to have this very soon. So mostly with the Joan Miró telescope, the 0.8 meters, for about 10 years, the team has been contributing very actively to follow up of Gaia science alerts with like 183 sources with different passbands, about 30,000 images uploaded, which resulted in several papers about the objects that you can see here. So the team has been very active into like supplying additional photometry. And as my, let's say, personal contribution, here is me as a PhD student in the science alerts team, I also made some predictions about what Gaia should see. So here in the plot, you see a distribution of the redshift for different supernova types that were predicted that Gaia would observe per year. I mean, mind the numbers. I don't know if you see them, but it's like 800, about 100, and about 4,000 of like type 2s. So like, well, did we see them? This is an important thing to see if we can verify what we expected for Gaia to become. So here I would like to introduce you like some of our recent work in our group, which is a galaxy catalog. So if you want to know what transients correspond to like supernova and extragalactic transients, you need a good catalog, hopefully a unified catalog with distances, because that's also very important to know kind of the redshift or the distance of your object to know how luminous it is and where you should classify it. So yeah, at the moment we have like 80 million of galaxies up to 2 gigaparsecs. And the most important, we have these distances, either photometric redshifts or spectroscopic redshift. We have colors. We have also the inferred stellar masses for these galaxies. And we also have the ellipse, which determines like what is the location of this galaxy on the sky. So then you can do your own cross matches. So also human vetted, wet neural networks. We kind of looked at all the galaxies closer than 100 megaparsecs to discard obvious contaminants that were normally slip into these images. And we are almost complete for Milky Way-like galaxies up to 350 megaparsecs. So we did the cross-match with the Gaia alerts with this catalog, and we resulted in like about 33% are matching a galaxy. So this is how the catalog works, and this is a small intermezzo. Priscilla mentioned that yesterday that they discovered this transient, which kind of looked like a supernova, but here in this catalog, you see that indeed there are 2 different galaxies, and this is the one centered on their source with a separation of 0 arc seconds from the nucleus of that galaxy. So, now if you use this catalog, you immediately see that's in the core of a galaxy. And yet an additional case targeted to Nada's talk yesterday. There are 2 more objects that she presented that are TDEs, and you also see that the separation in arc seconds to the cores of the galaxies is 0. So I think this can be a tool, right, for you to use to discard, like, a supernova or like the target tidal disruption events, for example, or distinguish whether it's a galactic or extragalactic transient. All right, so after cross-matching with this catalog and using the classification either from the Gaia Science Alerts website or the TNS, we see that we have a fairly similar distribution. I must say I'm very impressed. That the actual kind of histogram of redshifts, it follows pretty closely the expectations that we had, but the numbers are lower, right? So if we check how many objects do we have? I mean, the number of supernova here was about 900 per year, but now in total we have classified 2,000. So, there is a big bunch of unknown objects, and this is a problem, of course, because if we don't have a spectrum, we don't have the chance to know what they are, but well, maybe there's BPRP spectra. But of course, we discover like many other objects like AGN and superluminous supernova and TDEs as well that go into this chart. So we need to take into account that, Gaia has been operating, but the amount of transient discoveries has been like ramping up over the time. So you cannot assume that it had like full potential discovery from day one. But I would like to pose this as an interesting thing to do when you have like DR4, for example, with BPRP spectra, that we know it has been used to predict the supernova types. So basically, this is a nice little project to do when DR4 comes in. It's basically try to match the expected numbers that we predicted for Gaia discovered supernova. All right, so after all this big Gaia adventure, like what have we learned? Well, first of all, is that space missions have several advantages, of course, otherwise we wouldn't go to space. We have no atmosphere, and that results in like much higher resolution on the one side, like no weather gaps. And then we also can get closer to the sun. So Gaia has been discovering objects that were much closer to the sun that we can see from ground. And also, for example, it has access to other wavelengths. But it also has taught that space missions can be difficult, especially if you have limited memory on board, you cannot transfer everything. So Gaia chose to place these little windows and just transmit the windows to ground. But then catalog matching was very difficult because it's a real challenge to match something that you cannot really see in an image. So understanding your data and the way you're treating these cross matches and these catalogs is very difficult. And also, as we heard from Simon, like the design of the database is very important. So based on that, like the cadence also showed us that likely we need complementary information from other catalogs, either archival catalogs, stars, galaxy catalogs, AGN catalogs, but also complementary photometry such as the BHDOM is providing us so that we can properly follow up our events. And finally, spectroscopy is key. When we don't have it, then we cannot properly distinguish which kind of events do we have. So with this, some of these things in mind, I would like to introduce you FOTSat, which is the first Catalan kind of astrophysical satellite. There have been some missions before, but they are looking at the ground, so they're Earth nanocube satellites, but this one is looking into space. And it's led by this IEC, kind of this umbrella institute, which collaborates with all the other space institutes in that area. So some of the science drivers is basically to provide homogeneous coverage in the UV and the visual bands. So this is something that we really wanted to exploit as you go into space. You get access to UV wavelengths, that this is unique. So this will make this mission really, really unique, because then you can provide data that from ground you're incapable of providing because of the atmosphere. And then it's great because we are complementing other like big past and current missions in a different ways. So on the one side, Galax, for example, you can see a plot here, becomes kind of non-linear at about 50 magnitudes. And that's kind of the range where we are gonna stop. So basically the things which are brighter than 15 in Galax will be non-linear. But for us, this is the range where we are gonna provide you the photometry. Then LSST as well. I mean, we've been talking about LSST, but LSST saturates at 15.8 magnitudes. And I believe like most of the objects of interest for this audience are actually bright targets. So basically LSST will not work for your bright targets because it will be saturated. So then with FOTSat, we can actually reach 50 magnitudes, and we can provide you like kind of time domain photometry for brighter objects, which are also much nicer to follow up. And finally, variability in the UV. And this is, again, like the key of this mission, because it will be kind of a 2-day cadence on hot objects that otherwise did not have this photometry before. I mean, Galaxy is like 1 or 2 epochs. Then we have Swift, but it's also targeted. So this is a whole sky variability in the UV. And there is a great wealth of science, like white dwarfs. Also, there is this hunt for these stripped binary companions that are only now are starting to be detected. Or exoplanet transients are on like hot systems. So yeah, the coverage is going to be complementary to this current missions like ZTF, LSST, or BlackGem from the south. But also this UV will allow us to early detect things that from ground it's too late, right? All these hot objects like superluminous supernova, very young supernova, TDEs. I mean, they all start kind of in a very hot regime where you have most of the UV flux. And by the time they come into the optical bands and you are detecting them from grounds, you are late. So you can trigger your SWIFT, but you are late, okay? So in this case, these UV data points will provide us the very early data on these very hot objects. And also, of course, like as we are scanning a lot of the ecliptic, is like solar system objects, near Earth objects, on all these also space debris, and because we also making some statistics about images like solar particle detection and cosmic rays. So the goal, the general goal is to obtain this simultaneous epoch UV and optical photometry for stars brighter than about 50 magnitude in the optical, and also early discovery this astrophysical transients during its 2 to 3 years lifetime, which kind of depends on the orbit. So we are expecting to characterize about 33 million stars with about Gaia magnitude brighter than 15, which will include about 500 or 900 close bright white dwarfs. And also based on statistics from the transient name server, which we know that doesn't like to report kind of galactic objects, at least we'll discover about 300 transients per year, which are going to be bright. And also many M-dwarf flares, which there was a team that wanted to alert immediately on them because they're very short UV flares. But due to budget constraints, we are not be able to alert on them, but we could discover them and make some statistics. So if you see the timeline, it will be complementary to other kind of space missions, such as Plato, for example, that also makes time domain on like bright regime. Vera Rubin, which, as I mentioned, will saturate in our regime. And also I would like to mention Ultrasat, which is another UV time domain mission, which is going to be launched towards the end of 2027. So we may coincide in time, but they are going towards much fainter objects. And ZTF, I don't know if we will kind of be contemporaries, because I know that one of their phases is finishing, so it's still funding pending if they will continue. So here I would like to introduce the payload. It's 2 telescopes, actually. One is operating in the visible, another one in ultraviolet. And we have 3 different passbands. So the UV passband is this one. It's kind of near UV. It's not very far because of our detector. And then we have 2 passbands, the red one and the white we call. But then if you do, let's say, white minus red, you get kind of this bluer, greener color. So you can actually have these simultaneous colors for your stars. So then we do exposure times like 3 seconds per frame, and then we co-add them to reach 50 seconds, and that's been downloaded to ground. But then we keep the statistics of these 3 second frames to do all the cosmic ray science. Our pixels are big. It's like 14 arc seconds per pixel, but I would like to remind you that, other missions can be in that regime as well. So for example, TESS is 21 arc seconds, and it has been great science done with TESS, or Assassin is about 8 arc seconds. So, I mean, we are in between these 2. So, I mean, even the pixels are large. I mean, our objects are bright. So I think everything will work out. So the 2 telescopes are basically here. We have a siderostat. This is the camera, and basically there's a mirror here which kind of rotates, you will see now. And this is a 12-unit CubeSat. So it's powered by solar panels. I mean, the look may remind you a bit of Gaia. We have these solar panels on the one side, which are always going to be facing the sun, and the telescopes are on the other side, and they are also kind of protected here. So how it's going to operate is basically there is an angle of avoidance to the sun. And basically then the siderostat is going to rotate with some tic-tac pattern, like a clock, the arrows on a clock. And then it will integrate and then kind of make a move and integrate and make a move and integrate. So every time we move like half of the field of view to kind of have some overlap. And then basically the satellite is going to make a slight rotation on the great circle. So here there will be like a node of high density observations, but then all of these will provide kind of like exposure to new area of the sky. So this is a very recent video, just a couple of days. Hope it works. Yeah, so here you can see this siderostat design, and it's kind of rotating, so that's what will happen. But yeah, that will be every 50 seconds. So then the orbit is a low Earth orbit, about 500 kilometer, and we are going to be constantly in this twilight region. So basically one side of the satellite will point towards the sun all the time to get the power, and then the other side will be facing the stars, and like as the Earth rotates, we will continue to orbit. And here you see the two, I think, yeah, this is another video that kind of shows the pattern of the rotation. And here there's Svalbard and Monsek, our own observatory, which has a radio antenna, so we can actually download the data from two different sites. Yeah, here's just an example of the scanning glow. So here you get the nodes, but then you basically cover all the sky in a great circle. So this is the setup of our detectors. So the UV telescope has its own detector. It's only devoted to the UV. But the other one has like a split filter pattern. So basically the white kind of coating is going to be put here and the red one here. So we actually do this kind of chess pattern. So if this is the sky, this is the first time we see it. So some stars are seen with this red filter, some are seen with the green filter, but then because we are rotating like half field of view, then the same stars are going to be seen with the other filter, and so on. So we are going to cover kind of this, the sky with nearly simultaneous colors. So here's a simulation of how the spacecraft is seeing, and this is a high density field. You see the number of stars. And this is a simulation. We have a simulator that kind of takes the Gaia catalog and it simulates what the satellite is going to see. And this is some predictions of how many stars we are going to see. I mean, our aim is to go up to 50 magnitude. I mean, if then there is some problems of stray light or other unexpected circumstances. Here is also some statistics for 12 magnitude, but our expectations is, yes, about 30 million of stars, which are seen in the Gaia with G-band. This is the observation density. This is just the first days of mission. Here we see that there is a high density node of observation, and then as the mission progresses, this high density node is going to be kind of moving in the ecliptic plane. So we're going to see a lot of asteroids, but I mean, most of the bright ones are known, but we hope to make a discovery. And these are the download rates. As I mentioned, there's the Svalbard and Monsek. So we can actually, with the compression rates that we have right now, we can actually download everything. So this is a system overview, and this is a bit complex, but just to show that the payload, and we have contractors from industry, which are going to handle this part, but then all the data reduction is going to be held in our own institute because I don't know if you knew, but Barcelona was one of the big participants in the initial data treatment and the updates of astrometric parameters. So then we have many experts who have worked on Gaia before. So this is really valuable lessons learned then to make FOTSAT, which is kind of a downscaled version, a success. So we also simulated variability and supernova, and well, thank you, CU7, for providing us the coefficients that we can reconstruct light curves. So for example, we didn't have to do much. This is just a comparison of assassin light curve of RR Lyrae with a reconstructed kind of Gaia from just a few coefficients. So then we can input already these variable stars in our simulator to then test our pipeline. And we can also inject some supernova from like known supernova templates. So then our group, and what I'm responsible for, is to generate astrophysical alerts from ground. So we download all these pixels. So we download full images. So now we have the advantage that we're not dealing with catalogs, but we can use kind of traditional difference imaging techniques, which are used in ground-based telescopes to detect these alerts. But the problem is like our pixels are very large, so our images are kind of undersampled. So for that, we are using a kind of a transformed version of the Zogi. I don't know if you know that, but it's kind of widely used among the community. But we are it's a new version which is optimized for undersampled data. So then we are adapting it to our satellite. And finally, also we are working on making an interface to kind of eyeball our transient and also distribute it to different channels. And here, I guess it's the debate, do we submit it to the TNS, even if they're galactic, to BHTOM, but maybe not all of them. So what is the limiting criteria or filtering criteria? And other brokers such as like Astro Colibri or others. So, I mean, we would like to know what is the interest, like who wants to receive these alerts and in what format, so we can like coordinate ahead of time. So lessons learned from Gaia and other time domains. So we have no weather gaps. We are closer to the sun. This is great. And we are going to use the advantage of no atmosphere to target the UV observations. So because memory on board is a limiting factor, but we are going bright, we can achieve high compression rates. So then we can actually download all the images. So we hope to solve some of the difficulties that the Gaia team had by just having kind of traditional difference imaging techniques to detect our alerts. And also we now have a great wealth of data that the Gaia team didn't have before. We have Gaia as a starting point, which is great, but we also have these galaxy catalogs, which will help us to determine what kind of transients we're dealing with. So then we really need to start thinking on like developing these synergies with BHTOM and other groups who are interested in receiving our alerts. And the finite spectrum is key. It's always key, is the most critical thing. So we hope that at some point we will have this 2-meter telescope, maybe not when FOD starts, but a bit later. But this is, it's going to be really key for current and future missions. So yes, my conclusions, FODSAT is the first CubeSat, Catalan kind of astrophysical Catalan satellite. The launch date is end of next year, basically, so it's fairly soon. It will deliver epoch photometry in the UV and optical for about 36 million stars with magnitudes up to 15, 2-day cadence. Then we are planning to make everything public, all the alerts public. And yeah, we would like to complement other missions in a way that the bright end is also the most exciting if you want to really study your events with high resolution spectra and other facilities that you cannot use for faint targets. So yeah, the exploitation of these science will certainly need your collaboration. So thank you.
Very much. That's super exciting. At least for me, I guess for everyone, but for me, having white dwarfs in my systems. So, Simon.
This is really exciting. Thank you, Nadia, for sharing. I have lots of questions, so some of them I'll ask you in coffee. But one for now, you showed us how the white and the red filter overlap half a field. Is the UV the other sidereoscope, and that's doing
that's what is always there. So yeah, that's a kind of imaging always UV. So it also rotates half field of view, but it's like another UV exposure of the same stars, basically.
So one of the things we learned with the transients, with the Gaia alerts, is we did not use machine learning for the classification. I know IPTF, PTF, ZTF, all of those did use a real bogus machine learned algorithm to help them get rid of the obvious garbage. We did not do that because we found other ways to filter. And you talked about eyeballing. Have you considered using something like a machine learning algorithm in the process, or are you trying to avoid this?
No, I mean, I think machine learning is great. I mean, the thing is like we still need to like an interface. So yeah, we submitted a grant to get a person to actually kind of adapt actually an interface we developed for BlackGem, but for FODSAT, which can actually allow us to see our discoveries. Because I mean, one thing is like you have a machine learning as the first step. So it tells you this is very garbage, or this is like not so garbage, or this is great. So then I think this is the first filtering step. We are also planning to do that because I mean, all difference imaging, there's many artifacts, as people probably know, like, spikes from bright stars, ghosts, reflections. And this is very easy to recognize in an image. So yes, definitely machine learning will be there. We have all the kind of the chain of machinery developed already for BlackGem. So it needs just a training set. And the training set initially will come from wet neural networks and some eyeballs, yes.
Yes, Nada. Sorry, my question is not about the CubeSat project, but about your ground-based 2-meter telescope. The question is, do you get these telescopes from the shelf, or you have to construct it by yourself?
It's
or?
almost from the shelf. I think it's an Austrian company,
Yeah,
which makes them, yeah.
Probably, yes.
Exactly. So they are good at doing this. We don't want to reinvent the wheel. We just want one off the shelf. And the key will be the spectrograph. So this is something that we want to design ourselves. So yeah, this may take a little bit more of time because there are still kind of discussions.
That's my second question, because you know there are many observatories in Europe which have constructed recently low dispersion spectrograph, and one thing which was initiated by Opticon is a kind of collaboration among observatories. Maybe we should discuss a bit further, because some design already exists. For instance, the Liverpool telescope, low dispersion spectrograph, we have made an adapted copy at Haute-Provence. So you could gain some time perhaps in discussing with all these observatories.
Yeah, no, because this is kind of a pan institute initiative. We already had a call for proposals for instrumentation. I was advocating something like SCDM. Other people want more resolution. So I think we need to converge on the final design. Yeah, but like high throughput, like long slit spectra, in my opinion, this is also the way to go. I mean, you can like, if you have a high throughput, you can actually reach fainter magnitudes. And in many cases, you just need one spectrum. So. Yeah, so but this is still under debate.
Okay, we still have time for questions.
How bright target you can observe, and what will be the duration of the seasons for some object? I mean, how many weeks during the year, because the orbit precession you can observe on objects.
Right. So I mean, it's as I showed, there's a high node of observations, which is kind of moving during the year. So in that node, you will have a very high cadence. But let's say outside of the node, like the lowest cadence you will have is about 2 days. So we can reach up to 50 magnitude in the optical bands with this wide and red. And for the UV, because the throughput of the filter of the passband is much lower, it's about 12 magnitude. Then the seasonal gaps, I have to admit, I don't know, because that depends on the sun avoidance angle. And yeah, I haven't looked into that myself.
6 magnitude stars, and could you follow object, for example, 2 months or something like this?
Yeah, certainly. I mean, like, I think like during like nearly the whole year, except some seasonal gaps when it's kind of behind the sun or very close to the sun. So yeah, it also depends on where the stars are, of course. I think our saturation limit, and this is something that we are discussing, because apparently the camera that they got has a very kind of limited gain, so you cannot tweak it. Bright stars are going to saturate, but then we are also discussing a potential way to avoid this by reducing the exposure time every, let's say, week. So, you do a scan, and then it's a shorter kind of exposure time to get cadence on also much brighter stars, which would saturate otherwise.
Okay, and one last question, Fabian.
Thanks, Fabian Schüssler, from Paris-Saclay. So certainly we are happy to discuss the publication of the transients through Astro Colibri. There's no problem there. Maybe I've missed it. What's the duration of the mission? Or
It's 2 to 3 years, and it depends, because we're going to launch these satellites with one of these Elon Musk rockets, and it's going to be in an orbit, and it depends on how stable the orbit is, because we cannot make corrections, that it will eventually decay and fall on the Earth and disintegrate. So yeah, I mean, we hope that the orbit will give us enough stability for 2 to 3 years mission. But if the orbit goes not as expected, it may last for a few missions, because we cannot really correct and the satellite to launch it in a different orbit.
In very last point, you mentioned the data downlink, but do you have an estimation of the delay between the detection and the alert that could go out?
Yeah, I mean, Svalbard is visible nearly all the time, so I think it's just a few hours. I mean, yeah.
Okay, great. We are all looking forward. Thank you very much again. And while we'll be also switching to this computer, we will welcome Ruslan Kono for the last, which we hope is not the last project that we will ever have, right? So let's just share from here. Yes. Okay. So the stage is yours.
Okay. Can you hear me all well? Yes. Good. Yes, I'll be talking about the Large Area Survey Telescope. But before I talk about the project itself, I want to kind of go briefly over the philosophy for this project, which is this measure of the grasp, which just kind of tells you what is the volume per unit time in which your survey can detect a standard candle. And this depends on many things like the limited magnitude, exposure time, and so on and so on. I'll focus here on two things. One is that it's linear in the field of view. And it depends on the effective area to the power of less than 1. Now, empirically, we know that the cost of a telescope depends to the power of more than 1 on the effective area. Well, there's an important clue here. Let's say we want to increase the grasp by a factor of 2. We can do this via the effective area, in which case we have to scale it by more than 2, and then the cost increases exponentially. Or we can do it via the field of view, which is factor of 2, it's linear. And then if you do it just by building out a telescope, the cost also increases by factor 2. Everything is linear. So this suggests us that if you want a high grasp, low cost survey, the best way to do it is many small telescopes. How small can they be? Well, for one, we want to avoid the diffraction limit. So in optical, we should have an aperture more than 20 centimeters. And then we are making a large field of view small telescope. So we need to shorten the focal length, which will hurt our resolution unless we use smaller pixels. As an example, 30 centimeter f2 telescope, if you want a 1 arc-second resolution, you'll need about 3 micron pixels. So there's a technical limitation here. For example, sub 4 micron pixels are on the market only since 2019. So basically, this is the origin of LAST, which is exactly a wide field of view small pixel optical survey. It uses these Celestron 28 centimeter f2.2 telescopes with the QHI 600, which is 61 megapixels with a pixel size of 3.6 microns. So these two together give us a 1.25 pixels resolution in arcseconds in a total field of view of 7.4 square degrees. Now, what we can do is take 4 of these telescopes, put them on one mount, point them in a divergent manner, and we have a unit that has a field of view of about 30 square degrees. Now, in LAST, what we further do is have many of such units. So the first LAST node is currently being constructed in the Israeli Negev Desert. Once finalized, it will consist of 72 telescopes, so 18 such units with a total field of view of 530 square degrees. At the moment, 10 units are deployed and operational. And the total estimated cost for such a node is about $1.5 million, which is cheap, so including all hardware and construction. Now, if we compare the grasp and how it compares to current and future generations, so in this case, you have LAST of 48 telescopes. It's older estimation. You see that in this measure, it is competitive with the current generations. LSST, of course, dominates by far, just due to its depth. However, grasp is 10 times as high, and the cost is 1,000 times higher. Yes. So some advantages and disadvantages of this kind of design. For one, it's modular and scalable. You can add units, you can subtract units. Near to all components are off the shelf, so it's cheap. And if you wanted to, you can build the last unit in your own backyard. Failure points are very isolated. if one unit breaks, you still have the rest. You can keep observing. You don't need to shut down. It's easy to modify. You can add filters. You can add polarizers. And an example, the group of Anna Frankowiak in Bochum is using the LUST design to fit them with polarizers and make a polarization survey, like a wide field of view polarization survey. So each of the 4 telescopes has a polarizer at a different rotation, so you can take all the polarization measurements simultaneously. And then via relative photometry, you can get your Stokes parameters. Yes, so, but of course, there's many failing points. A lot of telescopes, a lot of focusers, a lot of computers. The failure rate can be high, and so it requires a lot of maintenance. But even more significantly is the high data rate. We have large pixels with large chips with small pixels. We estimate to take, with 70 telescopes, about 24,000 images per hour. So this will translate in the end to about 3.3 gigabits per second in data rate. So you need a very efficient way to deal with this data and to reduce it. And a lot of our work goes into this, but it's possible. Right, so last is a survey. So what we will do is scan the sky every night. What we do is we partition the sky in predefined fields. And then during the night, we visit the fields in 20 by 20 exposure. So we take 20 images, each one is 20 seconds, and we color them into a deeper image. And the typical limiting magnitude for such a cohort is about 20.8 magnitude. Clear, no filter, it's purely a photometric survey. And with 70 telescope, we'll be able to, with our visit exposure, scan the sky above below L mass of 2 about a bit less than 3 times per night. And then another advantage of the position is that, you can correct me if I'm wrong, but I don't believe that within this Asiatic gap, currently there is any large-scale survey, so we will covering a gap that is currently existing. Yes, so science goals, it's a survey, so we're primarily going to detect transients via the survey mode. We'll also do follow-up, gravitational waves, GRBs, neutrinos, and so on. You can do cosmology, you can do lensing, you can time delays, you can look for exoplanets, solar system objects. Anything that has short-time variability will benefit from the survey. Transit detection, we do via subtraction. The Zoggy method, we just heard about it. ZTF, for example, also uses the Zoggy method. We have a predefined fields. For each field, we construct a reference image. You see an example of a galaxy in such a reference image. You take it like maybe, let's say, a week ago, you observe during the night, and then you have the new image. There's a supernova in there. You have your automatic pipeline does a subtraction, and then you have a difference image where you just have the supernova. And then you run a hypothesis test across the difference image, searching for new sources, and then you have just extract all these significant peaks. So currently, our rate of transit candidates is like 1.7 million per telescope per night. So for 70 telescopes, this would be more than 100 million. Most of this is false positives. So you need a good weighting system. We use a fully deterministic weighting system right now, no machine learning, just a collection of hypothesis tests and heuristic methods. And this will be published hopefully soon. But an example of such a test is a recently published method, a statistic that tests for moving sources. Like a very common false positive source is poor registration. If you opt for like a subpixels, this might appear as a transient. So it's a statistic that tests if the source moved or not. And if you compare it to the new source statistic, you can make a distinguish what is more likely. You see, let's say on the right side, you see a plot that kind of shows what is more likely. Is the source moving, or you're going brighter for variable stars and non-variable stars. If it's below 0, then the variability statistic dominates, and the stars are kind of where it should be. So whenever we detect a transient, then we filter it, we correctly identify it. We report it internally to our marshal. Just a Tomcat marshal, very simple. Then we weight it by. We have about 100 candidates per night as a report internally, and we submit the TNS report. You kind of see how for this supernova, for example, we cover it fairly well, like every night. A note on our field of view, for follow-up for JRBs, GWs, neutrinos, for example. Here's a study, it's a bit older for 12 units. With individual quality of 12 units, we can cover during O3 and quotation wave alerts about 55% of observation no error for standard GW alert with 0.1, or 70 with 0.2 times, so we can cover the large uncertainty variable. Then a point also to show that we do the 20 by 20 in coordinations, but also the single 20-second images. Also provide photometry. Here's, for example, an envelope flare that was detected from all such cores, and within the single exposures, we kind of see a very extreme variability, so we can also provide very short-time variability. And then last will not be alone. It will be operational on the Weizmann Astrophysical Observatory, which will also have so we'll have LAST, and then we have FAST, and then we'll have MAST. So FAST is a color photometry instrument. It's 2 units of 4 telescope mounts. Each telescope is equipped with 2 broad filters. And then MAST is a multi-aperture spectrograph. So it will be 20 telescopes all feeding into one spectrograph. So we have photometry, color photometry, and this is the current drone picture of the site. See on the left is the current last enclosure. Where the telescope currently are, they will be moved to this new enclosure on the top, which will then also have 2 fast telescopes, and then we'll have 2 more enclosure forward. Current status, we are finalizing the enclosure for the 70 telescopes, plus the fast and MAST, full area by 2026. In general, we're operational, we take in data, we're producing alerts, have about 110 alerts, and in 1 year, we've produced about 1,000 TNS reports. We also do follow-up and write GCMs. Summary, last is an under construction cost-effective optical survey. Study the unexplored phase of transients, provide field of view, high cadence, and we will have dedicated follow-up instruments on site. Just some pictures by that.
Thank you very much. Another exciting project. Questions? David?
David Buckley, South African Astronomical Observatory. Maybe I missed it, but what's the depth that I'm expecting to go to? The depth, the magnitude.
The depth? It's about 20.8. Right? 20.8 man.
Simon?
This is a question for you, but for everyone, for all of us who are involved in generating lots of transients. And it's due because you're in the same institute as the host of the transient name server. And transient name server do not want us to submit galactic transients. So how are we going to manage the large numbers of galactic transients that you'll find going forward? Is there a solution to this problem?
Mm-hmm. So very
fair to you, sorry.
Yeah, no, it's a very good question that I've been asking myself and everyone around me all the time. I mean, so if I go back to this example, right? If you see a transient like this, high variability, it's galactic. I don't know what your report is to, but I don't know who's interested in it. Probably someone is. I mean, we talked with Fabian that we can use, for example, astrophysiology to next galactic transits to astrophysiology. If no one else steps up, and Fabian likes to comment. Yeah, Fabian.
Fabian Schüssler. Yeah, just to comment on that, we brainstormed in the coffee break that we could use astropolyp infrastructure to assign also names to galactic transients, right? And then publish them in our stream as usual. But I mean, we have ideas how to do that. We have a workshop coming up in 2 weeks with the hackathon. Maybe by the end of the year, we have something running. Quick question to Ruslan. You have these sub images or the individual images, and you mentioned the high data rate. You keep all of them on disk, so you can go back and have a look at the detailed light curve.
Yeah. So right now, basically, and we take images during the night, right? We calibrate them. We produce our science data, and this is safe. And then the raw images are compressed, and then everything is moved to an offsite cluster. Everything is safe.
Great. Thank you.
Okay. Nadia was first, Łukasz.
Nadia Blagorodnova from Barcelona. Yeah, going back to this MDOR flare. So actually with POTSAT, one of our main goals was to alert on these things, but because of these data transfer, gaps and so on, we are not going to be doing that. But I think if you can do it, this is a very strong science case, because like from our case, we need to send like Iridium messages to some of the satellites to send it to ground. And that it's extra budget, it's extra communication, but you have it on ground.
Yes.
So I think if you could alert, I mean, maybe then there would be a way to integrate with like POTSAT to to keep all those high, 3 seconds images and not stack them, just to send them to ground without stacking. So you can get the UV part of this, like for example.
This sub-visit photometry is basically when we calibrate, we process all the images. We do the photometry on the single images, and we make a catalog, and we just downloading the catalog. But yes, see no reason not to report this and so on.
Okay, the rest we will need to move to a coffee break. I have 2 questions myself, but I am not going to use this. So thank you again. It's very exciting. And yeah, we can keep it here. And our next speaker will be Paul Beck with Sonk Network. Some of you who were at the observatory already saw the telescope that we have here on Tenerife. So now Paul will. Yeah. Big. No, it's big. Yeah, there's no reason that's flying in the car. Okay, so the stage is yours.
Hello, I'm Paul, and I'm back, as the bad show goes. So today I would like to talk to you. Well, most of you have seen yesterday a certain telescope, and we have actually photographic evidence of that yesterday at the party. So if you have forgotten, after champagne, that's Tede and that is Song. And that's a group of astronomers that enjoyed the party yesterday night. So talking about this telescope, because actually we were there a lot of time, but we hardly talked about it. And I hope to answer some of the questions that came up yesterday. So first of all, I heard some consider seismology as black magic. Why do we need spectroscopy in a time where we have telescopes like Kepler, TESS, Plato coming up? Well, the oscillation modes propagating through the outer part of the star distort the atmosphere in the temperature field and the velocity field, which gives rise to what we call the spherical harmonics. And temperature fields can be detected with photometry, but the velocity field, which is actually much more fundamental because it's just a derivative of the displacement, they distort the velocity field, and we can measure radial velocities. That we can do for RLR stars where we have kilometers a second, and we can do it for solar oscillations, where for the sun we have centimeters per second. So, but there's a great deal of astrophysical information in there, and this is why actually SORN was built. So just to show you, this is actually the Golf data. That is the mission that was the spin-off from the Pyramid. For 30 years, we now have radio velocity and photometry data. And we can work with this by calculating the power spectrum. And the top one is photometry and the bottom one is radio velocity. And you see that, so this is frequency versus signal. And you see that the two, although they measure the same signal simultaneous, this radio velocity has a much lower background noise from granulation and convection. So basically, 1 month of radio velocity data has the quality of 1 year of space photometry. And there's even more. Okay, this is just to show that we can associate different components in the frequency diagram with different features. But why do we actually want that? Because taking spectroscopy, even a month, is very expensive. And those telescopes like Bright, SORN, they are not big. They're 1 meter. And they are built that they actually can reach the bright stars. Why? With bright stars, we can do high resolution spectroscopy. We can reach them with satellites like Plato or TESS. And you might have spotted a little satellite that is actually bigger than in real life. That's Bright, which is a Polish Austrian-Canadian mission. And we are very proud of our babies, I guess. And you can do for bright stars, you can do interferometry. So SORN is built for that target group where you can apply all 3 techniques to it. Now, what is SORN? As you noticed yesterday, we have this network. A Bison and Gorn are dedicated to the sun. But then there's a night component, which is the SORN, the Stellar Observing Network Group. Now, with this, and you see that those typically cluster at very similar locations. And with SORN, this is the logo, where the nodes are actually nodes. And those are the ones that are operational. The green ones are the operational ones, and the red ones are the ones that are being launched right now, built. So here we have the Tenerife node. Then here I have the zoom in front of me. Sorry, I don't. Anyway, you don't see my mouse anyway. Down there you have SORN Australia, then SORN China, and very new to the choir, we are having SORN at Apache Point in New Mexico, which is about to be commissioned late this or early next year. And the next SORN workshop will be in New Mexico, in case you want to go there. Now, those are the pictures of the different sites. The original idea was you have 1 telescope and 1 spectrograph to be as consistent as possible. And this spectrograph and this telescope, they are aligned with the mission requirements, meaning very rapid readout noise and short integrations. As you can see from actually the 3D printed telescopes, they look different. Because then, of course, reality came along and funding reasons. So sometimes in Australia, we actually are hitchhiking on another instrument where we attached fibers. China had to build it by themselves. So different reasons led to slightly different designs and also operational facilities. But yeah, the most productive one is the SORN Tenerife node, which we have been operating since 2014. And just nearly a year ago, in this very room, we had the SORN 24 workshop to celebrate the first 10 years of continuous scientific operations. So this is the SORN container in the crosscut. We have the 1.2 meter telescope. Then we have a coude going down into the box where we have the split, the slit container. Actually, last time we had a French student And she explained to me what Coude means. I don't know. Do you know what Coude means? I had 20 years without knowing that Coude actually means elbow, which makes very much sense when you look at this sketch. And there we have the spectrograph in there, which, oh yeah, and then we have the weather station on top and the webcam to take those pictures. Yeah, so the spectrograph is a high resolution shell spectrograph, typically operated at resolutions around 100,000, 90-some thousand. We have different slits that are available. We also have different calibration techniques like open spectra, then thorium-iodine sandwich, or iodine cell. And with this, we can reach precisions of 1 to 2 meters a second. Also heard at another talk the question about the readout. It's typically chosen as 5 seconds, but it can go down as quickly as 3 seconds to allow very limited downtime and optimize it for spectroscopy, for seismology. Then the time acquisition, target acquisition is going completely automatic. It's called the director, which you insert a table of object requests, but then during the night it is readjusted according to weather conditions, gaps, and yeah. So it was written by the SON consortium, and if it went well, this is how a good night looks, where we have one target being continuously observed for several hours, but around we had filler programs for all the programs that require longer cadences, not such a high consistent monitoring. And another night when we have bad weather, it looks like this. And then the conductor is taking care of all the individual settings and is going for the filler programs. Yeah, that's another one. The SON is a consortium. Each node member is part of the consortia, but the fifth node that I didn't mention yet is the Aarhus node, which was actually the design group with Frank Grundal, Mads Andersen, and Mikkel Lund. But also the IC has a big is owning 1/3 of the consortium, especially on Tenerife, so we are part of it. Just to show you a few examples with Sergio Simon Diaz is very dedicated to O and B stars, which are rapidly rotating, and that's why you can do very nice seismic studies with the moment method. You can actually see the distortion due to the oscillation waves in the spectrum. It's tremendous. You see the waves propagating. It's beautiful, and he's doing a great deal and also uses them as follow-up. Then we have, this is, I think, the most, at the time it was done, the longest, most massive heartbeat star, where we had photometry from TESS and also from RVs, which are typical eccentric binary. And then, okay, this meeting can't go on, I can't pass without me talking about Aldebaran, which is, I'm following this star since 8 years now with a nightly cadence. And what you see, this is the long periodic trend. And what you see in color, in blue and red, are actually the bright data. We use the Polnish bright satellite, and with this, and so we obtained simultaneous photometry and spectroscopy, actually multicolor photometry. And you see below the phase shift that we are having of about 160 degrees, which allows us to measure how adiabatic the outermost layers of such extended red giant stars are. And another project is done by Jejin on a subgiant. So this is but this is where all the recipes come together, that we can do space photometry and radial velocity to test things that are even more detailed than what seismology can do. And with this, and then we have also planets, of course, with this precision, we can do exoplanets, and which require longer sampling. If you want to become part of the consortium, it's easy. Just follow the QR code to what we call SODA. That's the Song Object Observational Database, I think. You just go to, you see new member, you fill it out, you select which working groups you want to be, and you have access to the data and you can request observations. If you have more interest in that, just let me know, talk to me. And with this is a typical sunset there, but I hope this is now working because just on the weekend we went up and I wanted to have some memories while I take your questions. Thank you.
Thank you very much. That's not from yesterday. There are no people. It was super crowded yesterday, no?
Yeah, that's
So-
actually from last night, from Saturday, and we could see that the sun was going down here. And a few degrees to the left already yesterday. So this is all the everyday astronomy when you see that.
Questions? Paweł?
Nicholas Copernicus University in Durham. Thanks for this talk. In order to get such a nice precision in radial velocities of the order of 1-2 meters per second, you have to use precise wavelength calibration, right? What kind of technique do you use for that?
So those are the modes I mentioned. We have thorium argon sandwich, which typically is, I think, goes down to 10 meters a second, but we keep the spectrum intact. So we can do a full analysis. And then for the 1 to 2 meter precision, we use an iodine cell.
Iodine cell, okay.
Yeah.
Thanks.
Okay. Milena?
And following question to Paweł, what's the limiting magnitude at every of those calibration techniques? I mean, what are the faintest targets that you can get with that precision?
That is a bit the downside. We're limited to 8th magnitude. But with this telescope, there's a program by Carlos. Is he here today? Not yet, okay. But he's a participant of the meeting. He has a program that every star brighter than 8 is at least once or twice being visited by song. So we have a large database for that, and it's completed the program. Follow up, because we would like to extend that, and there are currently efforts to get a fiber-fed spectrograph. I didn't mention the sun is actually located to SONG, and this is fiber-fed. But now the SONG telescope for the cell observations it's an experiment, but I think the New Mexico node will be fiber-fed from the beginning. So we hope to push the border.
Okay, and a very last question of Simon.
Thank you. Very quick question. It shows I wasn't paying attention at the beginning. What's the wavelength coverage of this every star brighter than 8th magnitude spectral atlas? That sounds amazing.
I'm going there. Give me a second. I had it. Yeah. 480 to 780 nanometer. Yeah.
Okay, we can move the rest for a coffee break. Thank you very much again. And I don't know if that was on purpose that we have last song Gotha of David Buckley. We're very creative. This is actually nice, David. With the names of these surveys, it's not a very large telescope or something. So now we have David Buckley with Gotha.
Thank you very much. Yeah, so this is something which really only started about 10 months ago, this concept, which is being led by China, by the NAOC. And it's a sort of a adaptation or expansion of an existing program that began in China to basically have an array of telescopes to high cadence transient discoveries. So I think we're all familiar with the increasing number of capabilities that we have in terms of transient discovery space. And of course, the elephant in the room now is the Rubin Observatory LSST, which will be coming online, properly doing its 10-year survey towards the end of the year. But that facility itself is still limited in terms of what a lot of us would be interested in, which is really going to much higher cadence than what Rubin can go to. Rubin will sample the same part of the sky every few days, maybe in one, maybe in two filters. But what we really need is to be able to push to lower cadence. And this diagram on the right, we've seen versions of it in the meeting already. And basically, it's a luminosity timescale diagram for different types of transient phenomena. And so this array, which I'm talking about, is pushing to high cadence over the entire sky, all 4 pi steradians of the sky, north and south, to a depth of something like 21. And that may sound a real challenge, and it is, but this project has begun, and it's envisaged to be a global open telescope transient array project. And the reason I'm talking in this meeting is just to advertise this as something which you may hear more about. And if you have an interest in this, hopefully you will like to hear more, and we can talk about potential collaboration. Of course, it will cover many different types of transient classes. And I think for some of the ones, the high energetic ones like supernovae, kilonovae, GRBs, getting observations very early on, even before they've got to maxima, is actually crucial for understanding the astrophysics of these systems. And so that's one of the drivers to push to high cadence. But that comes with different compromises in terms of how faint can you go, how fast can you go. And so this project, as I said, is going to 1 meter. Well, I haven't said yet, but the idea is that there'll be 1 meter class telescopes, each of them covering a large field of view, namely 25 square degrees. Doing this with newly developed large CMOS cameras that have been developed in China. And so then the idea would be to distribute 135 of these telescopes at different locations in the globe. And that's just a nominal map there showing perhaps where some of these may be situated. And just in terms of the capability of the coverage in terms of timescales and so on, that diagram at the right there shows the cadence versus detection limit that we would hope to get with this array. So the idea was that these telescopes would be dedicated to one single filter because they're basically a modified Schmidt design. I'll just skip to where that is shown. So this is the camera that's already been developed for the first 2 telescopes, prototypes that have been developed. So these are 9K by 9K, 10 micron CMOS detectors in a 2x2 array that allows the whole field of view of 25 square degrees to be covered in one exposure. And the first telescope has been in operation now at the Jinglong station where Lamoste is by the NAOC for about 18 months and using this camera. The idea is that by the fact that your economy of scale producing many telescopes like this, the idea is that we may actually try to design these to go within a container as well to make them easy to deploy at different sites. Of course, the real challenge is going to be in scheduling and in the whole control of the data flow. And so there's a very large component of AI in this program led at the Zhejiang lab in China that have a group working on AI in astronomy. And already this prototype that's been operating has already generated quite an amount of data. There's examples on the right there of light curves that have come out of this survey, which has so far covered these fields that are shown in the middle there. There's also other smaller scale telescopes. There's a smaller aperture 30 centimeter telescopes that have been in operation. And there's a special issue on this in research astronomy and astrophysics if you want to hunt that out. I just wanted to also mention this rather novel and I think quite revolutionary idea that has also been proposed out of this group, namely to use narrowband imaging to determine radial velocities of stars over a wide field of view. It's a very clever technique that was published earlier this year in Science China. Basically, what it uses is a filter tuned to, say, the wing of a strong absorption line. In this example, they used H alpha and the spectrum of the object, which happens to be a white dwarf subdwarf binary with a 100-minute period. The spectrum is shown in the left there in the black figure. And there are two filters, not even designed optimally for this this idea. Optimally, they would be more box-shaped filters, but these were just filters to hand, which were basically redshifted H alpha filters for people that work on galaxies and so on. But nonetheless, they proved this by this technique, which is just taking the flux of the red wing of the H alpha line and a line-free region, the red and the yellow that's shown there. And you get different light curves as the line moves in and out due to radial velocity variations. So the top middle light curve is the one that's coming from the red filter, and the yellow one is the one that's coming from the yellow filter. And that is basically, the yellow filter is just the ellipsoidal variations of this binary star, but the other one is also affected by the radial velocity. And so by ratioing those light curves, you get a surrogate for the radial velocity curve. And that shows, the bottom right shows the actual radial velocity curve determined for this object using the Palomar and Keck spectrographs, and the surrogate of the radial velocity curve determined by this method. So this is a very powerful potential technique to look at bright stars over a wide field of view where you get hundreds of radial velocity curves just from narrowband imaging. So this brings me to the end of the talk. I just wanted to mention the fact that it already has become a global project within what's called the BRICS Astronomy Consortium. Originally, BRICS stood for Brazil, India, China, Russia, and South Africa. But it's now expanded to other countries, which include, I won't go into them, but there's other countries now involved in this. And we've sent a letter of intent to establish some of these, what we call prototype telescopes or pathfinder telescopes at 2 observatory sites within these countries, namely Brazil and South Africa. So there's a lot to do in this project, both hardware and software. And of course, I mentioned the AI embodied telescope technology. And so this will be a major challenge. And so the more people who would be interested in participating in this, the better. So I'll end with this slide. And I hope that you may find this interesting and come and talk to me about it. Thanks very much.
Thank you very much. Now we have time for questions.
Interesting. I'm interested in that technique of getting velocity. Since oh no, it's better. The radial velocities from light curves. So it's going to be taken for the brightest star, although the brightest star are very often massive stars which rotate pretty fast. So it means that Balmer lines are very broad because of the rotation.
Yeah,
Do you know with that?
if you're interested, I suggest you go and read the paper. They've done a full modeling in terms of different spectral type stars. So both effective temperature, log G, V sin I, all of those sort of things. And, you know, it depends on what spectral type is, what precision of the rate of velocities you can get. Of course, it can be complicated by intrinsic line changes and things like that. But for this sort of basic technique of looking like binaries, this, I think, is potentially an extremely valuable technique. And as we all know, the bottleneck for all of these imaging surveys, particularly LSST, is we don't have enough spectroscopic time to follow up everything. And a lot of that spectroscopic time is often to look for rate of velocity. So if you can do this just with an imaging telescope, you have really started to break that sort of tension that you just don't have enough follow-up time.
Simon?
You probably said both these things, but I can get them. What's the plate scale you get?
I was just trying to remember that before the talk because I thought someone's going to ask me what the plate scale is. Oh, yeah. It's a Schmidt, so it's very fast. It's F1 point something, I think. I can't remember. All I can tell you is that with that camera that I mentioned, the 18K by 18K, it covers the whole 25 square degree field of view. So I think when I did the calculation, about 1 arc second per pixel or something
Guessing
like
about
that.
an arc second, but I'll do it back of the envelope. And the other thing is, when are you gonna do it by? Your Pathfinder has started, right? So do you have a timescale in mind?
I think this is a decade long, or I mean, there's a lot of imponderables at the moment. I think we know there tends to be sort of things that happen in China and signs that suddenly happen. Decisions made they're going to do something, and in a few years there's a facility. You know, FAST is an example of that. I really don't know, Simon, but all I can say at the moment is within the NAAC, it's a high priority project. They've already produced 2 telescopes. They're committed to produce another 3 smaller ones, 0.5 to 0.7 meter, which will go to these other sites outside of China. They have an extremely good site in Linghu in northern Tibet, where they're putting the second prototype, where they're going to actually build the 14.5 meter segmented mirror telescope as well. It was recently approved. But yeah, I can't say what, you know, like, I mean, it hasn't really officially begun yet in the sense that this is still a Chinese plus BRICS project. It's not become truly global at this point.
Okay, and one last.
Yes, you raised an interesting question about rapid photometric variations. So my question is rather for the Gaia people. When an object is crossing the field of view of Gaia, you have 9 CCDs in a row with a time scale or whatever, 4 seconds or something like that. Has anybody tried to attempt to see whether you have photometric variations from one pixel to from one CCD to the next one?
And I think that's a question more for Laurent. So let him answer.
Yes, so within the group 7, we are analyzing variability from CCD to CCD. And so we have obviously some cases that was already published where we see the eclipse of an eclipsing object where you see a trend, and I would say also it's important these 9 CCD measurements, in addition to the BP and RT, which are following, that you can see if there is, for example, very short time scale event. You have one measurement is what you can see if the group is coherent or not. And so we have a certain number of metrics to detect if there is variability within these measurements.
So can you do that, David, these time scales?
Well,
Seconds?
yeah. I mean, these CMOS cameras can be run quite fast if we want to do that. And I think the idea would be we would try to have an intrinsically high time resolution. Of course, we might then co-add the data to get the depth. Yeah.
Okay. So let's leave the rest of the discussion for coffee break. And thanks, David, again. Release this. So for the last speaker, it will be Sharunas Mikolaitis on the risks and opportunities, or the vice versa, no? Opportunities first. So let me first download that. Yeah. And this will be for you. So for switching this, so this is. So it will be a slightly different talk than different style of talk that we were doing before. So okay, follow, yeah. So opportunities and risks for small telescopes, and we operating the small and medium-sized telescopes in all the networks, and actually we have to think about also what risks we also have there. So our team who came here is from, yeah, he's from Vilnius University, Faculty of Physics, Institute of Theoretical Physics of Astronomy. You see how long is the name. And we're operating the observational base in Mollet Astronomical Observatory, which we are very happy about. And I will base my talk on the experiences that we have there. So the weather in the north is not perfect, but anyway, when the skies get clear, we start to observe. So, and when I talk about the opportunities, so nowadays we are facing with the revival of small telescopes, small observatories, observatories located in strange places, like in the north, where the weather is very bad. Why it happened? Because the infrastructure and devices, connections became much more accessible, even from the small telescopes. If you would think what instruments we can have now in the small telescopes, those instruments were obvious for the bigger and larger observatories a number of years ago. So here is our observatory. We have 3 operational buildings in the and we are located in the fantastic place in the regional park with lots of lakes and mosquitoes around. We are operating 3 telescopes. There is the largest one, 1.65 meter telescope, Maksutov style telescope, and the newest, what Lucas said, the beast is 80-centimeter telescope. We can join networks. We are joining networks. We're participating in many networks, like our observatories participating, for example, the first 3, and we don't. But it is possible at the moment. And we can make a huge amount of new science in all the small observatories. Like, for example, 10 years ago, we got the very nice high-resolution spectrograph, and we were performing a number of spectroscopic surveys that were based on the bright test targets, the possible Plato targets, and nowadays we are working a lot with the chemical composition of stars. So like talking about abundance of specific elements. Other 2 telescopes that are equipped with photometric instruments, they will be described by my colleagues later, so I will not go further on that. Our newest example is the project that's actually we were directly concentrating a lot on carbon, nitrogen, and oxygen elements in space, and we're scanning the sky with the bright targets. With a similar idea as a song, scan all possible bright targets that we can access from our observatory and get CNO abundances.
I was talking about our spectrograph, so just a small advertisement. It's very, very nice device, actually. It was produced by Yale University, and we're operating already 10 years with this instrument. The highest resolution we achieve is around 68,000. I think it's very nice. It's very much comparable to the best observed, probably best spectral, very, very nice spectrographs in the world, like comparing with UVES and Pharos and so on. So this example of the sun, the upper layer is our spectrum, and you can compare with other spectra for other spectrographs, and you see this quite nice spectrum. Nevertheless, in this conference, every polite talk must have something to show about the corona borealis, of course. So here I also show an example. So we have a couple of very nice emission lines. On the left side, you see H alpha line, which is, you see, very beautiful, and it shows lots of activity in the system. And then you see in the middle side, you see in the middle plate, you see emission oxygen line. So it's like a really nice thing. During the eruption, of course, we'll take the spectrum again. We'll share with you. Another nice example, another emission from the light pollution made not by people, but by nature, so aurora spectrum. So we also see aurora, very nice aurora features in the spectra, so emission features. So it's nice and easy to apply for observing time. So my advertisement for you, apply for example observing time on our telescopes and using this link over here. So we are getting nicer and nicer instruments in our small observatories. And with that, we are getting more and more responsibilities. And those responsibilities are coming obviously from light pollution. There is a very nice example of light pollution, unnecessary light pollution happening over there, especially with this blue light. This was like really horrible. So, and I will show several examples from the Baltic states. Okay, so you see that we have the Poland, we have Lithuania, Latvia, and then Estonia in the north. So we kind of have quite nice sky in a number of locations. But I will show you several examples. And here is a nice example from TART Observatory. Probably many people already have been there in TART Observatory in Estonia. It's fantastic team. They do fantastic science in the observatory. Very nice 1.5 meter telescope over there. Very beautiful, strange buildings for telescopes over there. Very, very beautiful and really, really great people. However, if you would see the location, they're located in very much urbanistic place. There are villages and towns around, and even the place where they exist, it's surrounded by streets and with lights. So that's, if you would think about the observatory, it would, in the Tenerife Observatory, you would even not think about that you would have streets with lights around. Another example, Latvian Observatory, Balbines Observatory, again, very nice people and very nice Schmidt-type telescope over there. They're located so close to Riga. That is that for them is, I think, it's very big problem. And if you would see on that panel, so there on the upper side, you see observatory, and there is a ski station. It looks like that, okay? And that is next door. You understand? So, and the ski station looks like that in this. I think it's a problem. And we have to think about those kind of things. So our example, Molėtų Astronomical Observatory, as I said, it's in a very nice place in protected area, regional park. We are still in the very sweet place. However, I must stress, even small observatories apparently need protection zones. And that is very, very important because we have interests in developments in the very immediate next door locations, like the ski station that you saw. And if we talk about documentations, so we have to rely on one or two documents standard documents from the CIA, IU documents, and examples from some other observatories. And that is another issue. So the only concrete document that you can really rely while building your legal build-up of the observatory protection zone is the CIA standard. Most other documents, even issued by the big institutions, they talk in very general terms, and that is very difficult. And that is very difficult to actually rely on afterwards. And if some observatory has any zone and you want to use the document as a precedent, it's very difficult to find that because they usually don't share online. Nice example from South Africa, they actually have very nice documents prepared and you can learn a lot of that, but that's a huge observatory, so it's very difficult to scale down to this our small observatories. So in our observatory, we actually have the legal basis for a protection zone. We have a law that protects our site, and we kind of constructed our protection zone according to the standards of CIA. Our zone is very small, only 4 kilometers in radius. But anyway, it is very important, and especially as I showed the example before, it is very, very important to protect our really immediate neighborhood, not to have ski stations just nearby. And if you would see the documents of the large institutions, like if you would try to discuss the protection zone things in the legal way, especially with the developers, try to use that. It's very, very difficult because the conclusions and statements there are very broad. So if documents have very, very broad statements, like talking about lumens and shielding recommendations, it is very easy to get the ski station nearby your server with all the lamps and parkings and stuff. So in practice, we need, and it can be very, very much devastating. And if you adopt all the documents in all the broad way, you can afterwards have very strong cumulative effect, and you can destroy your environment. So with our experience, what was very important, what should be very important, it would be very nice to have documents that would actually express very, very concretely how we would need to see how we would see protection zone around observatory without vague terms, and especially that no lights should be allowed in the very, very near vicinity of the observatory, and no large-scale dust pollutants should be allowed near the observatory. And we are facing those things in the small observatories almost not, I don't want to say every day, but every year. So this urbanization is trying to come. So if any of your observatory has any regulation, legal regulation, please share, because we need to learn from that. And have a nice guys.
Thank you very much. Now we have time for questions. So while you are thinking about yours, it is getting worse at your observatory. Can you see that?
Yeah, the thing is nowadays we have this LED technology for lighting. So it's very cheap to build any lamps anywhere. So people are kind of trying to make nicer yards and gardens, and you can see that. But we are still kind of having very nice sky.
Yeah, I have seen that you are in a dark location, but I have seen observatories where they're still in nice locations, but you can actually see this gradual increase, in recent maybe 20 years.
But with observatories, just one last statement. The thing is, observatory usually is in the very beautiful place, and that means that the infrastructure was developed for observatory, like in very nice road, Yeah, and that block is bringing for you urbanization. Well, that's very big list.
Okay. Nicholas?
One question, have you been in contact with other associations in Europe? Because, for example, in Austria, I know we have a very active community which also tries to make protection zones. I mean, not especially for observatories, but I mean like star parks. And have you been in contact with such associations or organizations or not?
Yeah, we are relying on the Dark Sky Association, and we actually are making documentation for the Dark Sky Park initiation in the zone. So yes, we do that. But from all the documents, there are those conclusions that we can say. That if you want to go to the legal way, so you need documents that are really clear. And we need, as small observatories, we would like to have like IAU as a shield slightly protecting us. So that's my conclusion.
Okay, that's a very important issue that we can discuss during the coffee break. Thank you very much again. Before you all go to coffee break, two things. We still miss presentations for after coffee break session. So that's someone who missed the deadline of yesterday. So please upload your talk as soon as possible. The second thing is regarding tomorrow's hackathon. IAC is asking us for passport numbers or ID numbers. So everyone who is coming tomorrow needs to give us ID or passport number. So you need to go to Paulina. She will be collecting those. Who will not give us the number will not be able to enter. The guard will not let you in. So everyone who is coming tomorrow needs to give us the number for the guard.
Before noon, please.
So do that during this coffee break. Thank you.
Question 7. Question 7. Yeah? You're after lunch? Before. Yeah. Really? Sorry, yes. That's not. Sorry. Yeah, sorry for that. Yeah. Cool. Okay. Yeah, okay. Yes. Good.
Thank you. Oh, but that's waiting for the slide. So we need to. Not This is top. You have not downloaded that. You close it. And because it was stuck. Yeah. But because when you open the poster, you close the. We'll just. Okay, can we check the SSCS slides? It should be downloaded. It's the poster. About space. Yeah. On this one, the satellite stuff, just go down. Okay, so there is some motion. Which bring download. All right. Wait, yes, but yes, the thing of problem says Google Notes. We don't have it. Satellite start. Just it's low to text document will be okay. We easy because it will appear. We don't have the email open, and I will not need to type it. Text document of the link. Yeah. Yeah, you are. That's why you close the job. Hopefully, directly. Please use these spare minutes to give us your passport number or ID number. We will not be allowed to IC tomorrow. Before we start, once again, I'm reminding all of you that if you want to go for Friday hackathon to IAC, it will not be here, first of all. We will, again, reiterate on this in the afternoon, but it is not going to be here. It will be at the IAC headquarters. And you cannot enter without providing us your passport number or ID number. This passport or ID, you will need to show tomorrow to the guard. So you need to have the physical thing tomorrow to show to the guard to be able to enter. So, and we need to have this at the beginning of the lunch break. So if you have not done yet so, then please do that at the very beginning of the lunch break, because otherwise, if we don't have this information, you are crossed out from the list. We cannot wait for forever. And with that, I think that I will be the one doing everything, switching. So
Switching?
not your slides, but this is not your slide, no? As far as I know, at least for rest of the week, you were Gabriela, no?
Yes. Okay, no last name, remember me?
Yeah, but that was Agata. Not you, no? So it's taking forever. No. So, and now we can start the.
We can't start until I learn this magic instrument. Okay. This way, that way.
Yeah.
Destroy.
Yes.
Okay.
So the first talk of the after coffee break session, it will be by Gabriela Stanek on the European Astronomical Society's small telescopes. Stage is yours.
Hello, everybody. Hola. I need to time myself because I'm a talker. So I'll try to stay within the 12 minutes. Yeah? You're like the Oscar guy that plays the music. And I start thanking my family. Okay, start. So I'm here to talk about our new baby. It's called EAST with double S, the European Astronomical Society of Small Telescopes. I don't have to tell you about small telescopes as you're mostly astronomers or academics. You probably know more about them than I do, no pun intended. So basically EAST, we are from Poland. The sky begins in Poland, the sun rises in Poland, so you get the name. Yeah, cool. We're cool. Okay, so what do we do? Oh, great. So we're an NGO. So basically we have the funding we have is through the ideas we have, and we have to ask others to help us out. And what we focus on is science and outreach. And I had this great talk last night after the volcano with a friend. And I asked him, how would you explain outreach? Because outreach is a wonderful English word that doesn't have the translation into Polish, perhaps your languages as well. And what we came up with is outreach is reaching out. So you have the word reaching out. We want to reach out to citizens. We want to reach out to astronomers. We want to reach out to everybody and join them all together. We want to connect them. And we want to share our knowledge, our data, our experience, and their knowledge, their data, their experience, and to make it a cool new place for astronomy and citizen science. So we have a global network of 130 telescopes. And as someone very smart pointed out yesterday, at least 4 of these telescopes are in Tenerife. So yay, it's all connected. We're all connected. So yes, this is kind of me repeating myself just to make a point, just in case you didn't pay attention to slide number 2. This is slide number 3, repeating slide number the previous slide. Advancing citizen science with small telescopes. So our strongest tool is BHNOM, which you probably know everything about and you can recite in your sleep, as Łukasz, Krzysztof, and all the other smart brains explained on previous days. But yeah, it's a tool and it's amazing. And us as EAST, as our foundation, we get to use it and teach people how to use it. So yes, outreach, reaching out, connecting, education, obviously, because we want We want to spark the enthusiasm and young people. Because someone said this to me when we were starting the foundation, that a lot of kids, I don't know how many of you have children, I do, they love astronomy as children. They're like, yeah, this is cool. This is amazing. Then they grow up and they hear, well, that was just a dream. You wanted to be a fireman, astronomer, and a movie star. Now you have to be a lawyer, doctor. Well, these are all cool professions, don't get me wrong. I'm a journalist myself, but yeah, we want to educate people to be able to enjoy astronomy on a higher level. Telescopes, network science, enhancing telescopes and data processing technology. I don't know much about that, but I'm sure you do. And protecting dark skies. I heard there was a great talk about light pollution from one of our Lithuanian friends. He's in the back, he's shy, he's working on something. Hey, don't look at your laptop, look at me. Hi, yeah. And this is us. So basically, this is the board. 3 of the people here, you know, and some of you might know 4 or 5 of them, right? Because this is, it's a small niche, unfortunately, we're in, but that's what ESA is trying to do, to make this astronomy niche bigger. So the first person you see in your top corner, I don't know if you know him, his name is Professor Łukasz Wyrzykowski, repeat that. Łukasz Wyrzykowski, and obviously he's a professor of astronomy, as you know, and the brain behind many of the amazing things happening in the past 2 decades. Let's not mention age. But what's really cool about us is that he invented BH-STOM. Remember BH-STOM? Yeah, BH-STOM. And since now he founded the foundation, so he can just fulfills and kind of expands the use of BH-STOM to amateur astronomers, to citizen science. We can teach people how to use this tool, we can popularize it. So yay for Łukasz. If you need to know more about Łukasz, I'm sure you can meet him over lunch and hear all his other amazing ideas. And then that's me. I don't know if you see the amazing profile photos. Mr. Krzysztof Kutysz took them, and that's why they're so pretty. I am not an astronomer. I don't know if you've noticed. I'm a journalist. I studied television and radio production in Toronto, in Canada, and then in Perth, in Australia. And I thought I'm going to make these documentary movies that are going to change the world. But then I came back to Poland and became an astronomer 20 years later. I don't know how that happened, but I guess the stars aligned in the right direction. So I'm basically responsible for all the stuff that's logistics, office calendar related. I don't get into the science. As Elton John said, it's just my job 5 days a week. Zbigniew Gajewski, which you're going to hear more from today after 2. For 27 years, he was a director of an elementary school that has an professional equipped observatory on top of it. I'm from Poland, but I have a problem pronouncing it. Bolencina. So, and right now, he's just our top brain, a really good spirit, a wonderful man. And yeah, he's on our board. And next, the beautiful ladies, repeat that. Elżbieta Łazarewicz-Wyrzykowska. Everyone. And she's a biblical scholar on the PhD level. So basically, she brings science and knowledge and faith, all of it together in her amazing brain. She's also a coach and leader, which is really important these days because we're not just, oh, I get a 5 in Poland, that's the top mark you can get. Oh, I have 5 minutes left. Yeah. Okay, so Elżbieta teaches us how to be better leaders. And personally, she's a dear friend of mine and a wife to Professor Wyrzykowski. Wieczysław Bienkowski, the guy with a really cool braid on his beard that actually goes up to his knees, just kidding. He's an astronomer, space industry, space safety, all the cool stuff. Yeah, that's us. The projects and events, I don't know if they're gonna mean anything to you, but they're really cool and they all happened in Poland. So meeting next May 2026, you wanna come to Valentina and be a part of the big May 29th, yeah? You wanna come to Poland in May? Yes, you do. Polish Astronomical Society meeting, that was last week because the Observatory and the University of Warsaw had 200 years. OMG, that's what we're doing right now. It's going to be really cool. We're bringing young people to universities, 5 biggest universities in Warsaw, and we're going to teach them how cool astronomy is. Odkrywcy, discoverers, teachers, BHM, this week. And that's just a collage of photos, and we're going to take another time. Well, that's us being cool and doing cool things. And remember, we're only 9 months old. We're like a baby. And we already have all these cool things behind us. And we're getting to the climax. We want people to join us as partners because we're this little foundation. Everybody to join. So, actually, look at me. I'm so minutes. I have a form you can fill out, or you can find my website to become our partner. Anyone can become our partner who's in this astronomical world. And what's most important, besides all the cool other stuff, is that we can do projects and grants together. As you know, we all work as volunteers in the NGO, but we do like money, as everybody likes money, but and to get projects and grants, sometimes you need to cooperate with international institutions and international academic people. So yeah, join us. We'll talk about it because I don't have that much time, and I have a content for you. Yay! Oh, look, cool ambassadors. You can also become an ambassador, but that takes more work because basically, once you're an ambassador, we ask you to spread the good message of the East in your country. You already have these cool, look, New Zealand is we, Turkey, Lithuania, France. Okay, and why us? Someone asked me why us? Because we're cool, we're unique, and we want you all to join us, right? So, and use the social media. We have obviously Instagram, Facebook, LinkedIn, and now I have a little contest for you. Everyone's paying attention. No one is in their laptops. Oh, well, I understand you have to work. If you join our Facebook, our Instagram, and our LinkedIn today, it's East with a double S. I have these beautiful, you're probably all wondering why I'm dressed so coolly. Look at this. We have these cool bandanas we've just made. It's a logo and it's purple. And if you want one of these, please join us. Show me you're a fan on Facebook, you're a fan on Instagram, and you're going to get one of those beauties. Yay. So basically, we want to do this all together. So either a partner, ambassador, sponsor, enthusiast, or just friend. And actually, in the morning, I try to say thank you in all the languages, the friends I've made so far. If I've missed your language, please forgive me, but it's great to be here and it's great to meet you and talk about different things from astronomy to volcanoes. And the question is, Tenerife, Africa or Europe, and why is it so cool? Yeah, that's my last slide. Look at me. I made it on time. Questions? Thank you.
Yes, exactly on time. So questions?
Yes, gentleman in the white.
No, there was a question first. Nick? Yep.
I wanted to ask about your fundings, like the fundings you gave out, because, for example, do you have some programs to fund telescopes for organizations like schools? Okay.
So we're applying for. So we were supposed to get this really cool fund from the ministry. It was called WOW in NGOs, and basically it would give us money to buy sea stars and small telescopes for a number of people. But we didn't get it because we started in February of this year, right? So a lot of these grants as a requirement, you need to be an experienced, it's like you finishing university, you're 25, but they'll give you a job if you have 20 years of experience, right?
Yeah,
So basically, that's why we want to partner up. We're just beginning, and of course, we won't buy everyone a telescope. Come on, you'll get one. Just be patient. We just need more funding. Yeah, we're waiting.
Because high schools are like a hatching place for young astronomers, young astronomy enthusiasts. So, and many schools in Poland, for example, have these domes that were functional like ages ago. So they just need that kick to.
Of course.
So
we understand that knowledge is important. We understand the science is important, but money is also important. Yes, so let's not be shy about it. So yeah, we're looking and we're searching and we're thinking and we're applying, but you can help us with that, because if you become part of us, then you'll care about it as much as we do, right? Good question. You'll get a telescope one day.
Simon?
My question just got asked and answered.
No.
But I do have a comment. So I'm very happy to see EAST as a formal organization, because many of us have been using BH-TOM over the last few years. And thanks to BH-TOM, we can get high cadence photometry in really near real time from an alert being triggered. And I don't have to write a proposal. I can just collaborate. So I don't have my own telescope. I would like to know in a more concrete way how I can contribute. I can be a friend, sponsor, enthusiast, but are there sort of more quantitative things that I can actually do I help you write grants, or what do I do?
Grants. If you let's say you're from Cambridge, I guess.
Yep.
So let's say you hear of an amazing project for young foundations, or something that combines your because you're in Brexit. Sorry, let's say you're.
We forgot that.
These wonderful people in Tenerife, and they have this foundation, and they do so much. And then you contact us, we do it together. Great, that's one way. Another way, what's another way? Oh gosh, what's another way people can help us be part of our team? Yeah, you can be a professor, you basically can go to the UK and be like, hey, I know everything about EAST.
Okay, I think this is something we can discuss maybe a lot of us during lunch break. So thank you again for introducing.
Don't forget about the contest. We have 20 to give away. I'm sure you all want.
And now we will continue in the topic of education and using the astronomy in education by Magdalena Skudlarek. This is a poster talk, so you have 3 minutes.
Hello, everybody. My name is Magdalena Skudlarek. I'm from Janusz Gil Institute of Astronomy in Zielona Góra in Poland. I will shortly talk about integrating time domain astronomy in STEM education. So actually at university level, research-based learning is already well established, but what can be a real game changer is engaging high school students, especially before they choose their final field of study. So by participating in citizen science projects, high school students can become real contributors to the modern astronomy. And these contributions can not only be part of ongoing science, ongoing research, but also they can create a sense of belonging to a professional community, professional research community. So I just also wanted to mention that BH-TOM is a fantastic tool. It boosts the professional research, boosts the new collaborations. However, because of its automatic analysis, its direct educational value is limited. So through projects like, through methods like project-based learning, hands-on science, students need to work with raw data. They need to struggle with it. So this actually, in my opinion, is the only way they can gain analytical and project-solving skills. So to that, we are using project like ExoClock, like Exoplanet Watch. We upload data to AFSO database. We also, at some point, we were involved in HOIS citizen science. So I don't have time to talk about them, so you can reach me at the break. But also I wanted to mention that you will hear a little bit later more from my colleagues from Zielona Góra. Michał and Tomek will have a contributor talk at the end of this session. They will talk about our telescope, about our project, about the automatic scheduling system that we recently implemented. We also have 2 undergrad students here. So Agata in a few minutes will talk about integrating of OCS with our telescope, and Carolina will talk about in a little bit more details about the ExoClock project. And the last lady is very stressed, so I will take to tequila at the end of this day. Thank you.
Thank you. Perfect in time. So now we have time for questions. Elena?
Thank you. So does it mean that you have it in your courses at astronomy? So you reduce raw data from the telescope, or how? In which course do you put this?
Well, at first we need to gather some high school students, and then we are just giving them our data, and we their results to the different databases. And at some point, for example, in ExoClock project, every contribution means that you will be a co-author of the publication.
Which is true for Black Hole Tom as well.
Yes, of course.
Any other questions? If not, then we can cross the border. Thank you again. And cross the border to German Center for Astrophysics. Konstancja Satalecka will introduce shortly the center and the activities they do.
So hello, everybody. My name is Konstancja Satalecka. I'm currently based at the German Center for Astrophysics, or Deutsches Zentrum für Astrophysik, DZA, which is located at the Polish-German border in Görlitz-Gorzelec. And I'm in the knowledge transfer and regional networking team. And you might ask yourself, okay, who are these people? We never heard about them before. And you are right, because we are there only since 2 years. And only since next year, we're going to be an independent institution. The whole idea behind the center is actually first regional transformation. So we won a competition by the German government to transform this region of Saxony from lignite mining, which you know as brown coal, maybe more popularly, to innovative technologies. And the way you do this for the ministry was whatever you want to do. And we want to do astrophysics. And we think that astrophysics is a great door opener for many other subjects like technology, innovation, education, but also important social things like diversity, equity, and inclusion. So this is all in our program. We are, of course, facing many challenges, and you might ask yourself, okay, why do you locate it there, like in Saxony, somewhere, nowhere? Well, actually, it's a great region to make astrophysics because there's a lot of tradition of astronomy in the region. Astronomy was an obligatory school subject till 2011 in that region. Then some people made some really wrong decisions and it's not obligatory anymore. But there's still a lot of very engaged teachers, a lot of schools who have small observatories at the premises, a lot of small observatories in the cities, planetariums, and so on. So there's a lot of infrastructure, a lot of people in astronomy clubs that are interested to bring it forward. And our centrum is giving them support, incentive, and the reason for the structures to exist longer. We are there, since 2 years. First, we have 2 people employed. Since April this year, there's 6 people employed in our team, so still very few, but we already run a few successful pilot projects. So the project that it's really super cool and always brings a lot of joy to everybody is the tabletop radio telescope, what you see on the left. It's basically a telescope that you can build with high school students during one-day workshop made of cardboard, aluminum foil, and a few electronic parts that you can buy for less than 100 euro. And it works. And you can see the 21 centimeter hydrogen line from our galaxy with this thing. And it's very popular also on the science fairs. Instant conversation starter. Everybody wants to know what that is and why. As we heard in previous talks, there are also some other subjects connected with observations that are very important. For example, light quality, light pollution monitoring, and weather monitoring. And we are bringing this also in the building weather station prototypes and also measuring sky quality in the sites in which we have our little observatories. These are all very early stage projects, but we tested these activities now with high school students, and it works pretty well. They have a lot of fun. They win first prizes in the school competitions for a science project with this, for example. So not bad. And I came here with a mission to introduce to you the Institute, what we do in outreach, and also to network with you, especially with the people from BHTOM, because we would like to integrate the small observatories, regional observatories in the BHTOM network. And I wanted to thank everybody because I've already got a lot of support from you, a lot of very useful contacts. So it's a great conference. Thank you. And yeah, you can clap to yourself also because you're doing a great job. Really. If you want to learn more about the Centrum, just visit our webpage. It's in German, English, and Sorbisch. That's a regional Slavic language. That sounds a bit like Czech with German accent. But yes, or you can use the QR code. And we are looking for new employees in all possible ranges from HR to astrophysics. So if you're interested, just look at our career webpage. Maybe you find something there for you too. Okay, thank you.
Thank you. So now we have time for questions again. Nada?
Hi. This is really great. It was really good to hear this. I had a question. If it's not too much to ask, by who are you? How are you being funded? I cannot.
I funded from a special fund from the German government for the regional transformation. So the German government decided to find two science centers in, let's say, the regions that were a bit neglected economically and socially in the recent decades after the unification. And you could apply for this funding with your ideas. And there's one chemistry institute founded in Tübingen, and we are the other one that does astrophysics. I have to underline this, that we had from the beginning on in our program, in the application, a very strong outreach and education component, which unfortunately the other institute doesn't seem to have at this extent. But yeah. Yeah, but this is government funded, and of course, we are open for any kind of proposals from EU grants and so on, interregional grants, especially with Poland and with Czech. We are very much interested with that, with Baltic countries, Ukraine and so on, to work in the region. And yeah.
How many scientists you have currently, like really doing science?
Okay, so we are right now slightly over 100 people employed, and out of that, about 1/3 are scientists, and this is going to be the ratio of scientists to all the employments that's going to stay. So our aim is to employ about 1,000 people in the next decade. 1/3 of this are going to do actual astrophysics. The rest is going to be administrative support, also average people like me, technology transfer people also. We want to do a lot of technology transfer. Yeah, technology development, for example, for ET, for radio astronomy. Yeah.
Great. So if there are no other questions, one more, Maven.
I have a comment. In this year, during the International Astronomical Olympiad for Astronomy and Astrophysics, the organizers built 20 1-meter size radio telescopes, and they don't give it to school, but they built something like a library of radio telescopes. So school should borrow the telescope and use it per some time. This is a good idea because the telescope not stuck in some schools and they all the time. The same idea could be used also for optical telescopes. So just library of small radio telescopes or of telescope. I think this is cool idea. And also the design of this 1-meter class radio telescope. I think it's maybe comparable to this one which you show. Will be soon published in web pages of International Astronomical Olympiad of Astronomy and Astrophysics. Also low costs. So okay.
Okay, great.
Thanks.
Yeah.
Okay.
Thank you very much for this hint, for this comment. We will talk later. Yeah.
Okay,
Great.
Thank you very much again. And now we move back, no? There is the same telescope as Magdalena was talking about. So we now move back to the telescope, to the operating system of a telescope with Agata Wozniak.
Okay, so hello everyone. My name is Agata Wozniak and I study astronomy and I'm from Zielona Góra. So today I will present my poster, Integration of Observatory Control System data with the Rotus telescope system. So Rotus is a telescope which is owned by our university, but you will get more details from presentation of Michał and Tomek, which will be before the lunch. So we are engaged in many projects, including BHTOM. So until recently, our observation requests were prepared manually, but now we decided to make our work faster and improve this a bit. So we decide to integrate. Sorry, I'm so stressed, but okay. So we decided to make this integration through observatory control system so that now we can send, we can schedule our request. We can schedule BHTOM targets directly on our telescope. So here is the implementation of our integration. So first thing we do, so we check which part of the sky is visible during the night from our observatory. Then we send a query to BHTOM API to retrieve the list of targets. Then we count the priority for each target so that we know which should be observed first. And then we can select any number of targets, and based on BHTOM data, we can, our script can generate and send the request to our OCS system. So then the observations are executed. And after that, I would say they come back to the OCS. We do some calibration, we do some reduction. And at the end, again, we upload our data, we send our observation to BHTOM automatically through our scripts. And here there's a screenshot from our observatory control system. So you can see that our requests that were sent automatically are completed. And here you have the plot from BHTOM. And I hope that you can see that our observation were also sent to BHTOM. So you can see that this whole process is working. Thank you.
Okay, so do you have a gaps between observations? If you have, what do you do then? Like the gaps, so time that there is no object observed.
I think that now we don't have this problem because usually you have some objects. So we will see in the future how it will look like.
Okay, thank you.
Thank you. How do you prioritize the targets? Because in the beginning you said that you know prioritization.
So Professor Byrzykowski sent us like the program that shows how they count this this priority for each targets. So that's how we know how to. Yes. Yes.
Piotr Bauer, NCU. Do you have like, if the upload to BHTOM fails, do you have like informations in OCS why it failed, or you need to test it manually to check if why it failed?
I think that we have to check this, why it was failed. But they can fail sometimes.
I mean, sometimes something's wrong with the data, and let's say that the Python script failed, and then you need to check why it failed. Then you check it in OCS, or you need to launch the scripts manually.
I would say that we have to launch the script manually and see what's happened.
Should not have all the mics on at the same time. So thank you very much again. It's very exciting to see how it works. And yep. And we now go back to Molokai, actually, with Erika Pakstiene on the search for black holes and other time domain things, phenomena, objects. Next time we do a hackathon on how to use the pointer now in the beginning of the conference. So the stage is theirs.
Hello, everyone. I'm Erika Pakštienė from Institute of Theoretical Physics and Astronomy at Vilnius University. Personally, I am interested in stars with solar type pulsations and their ages. But also I observe a lot at Molėtai Astronomical Observatory. And I observe all types of variable objects with variable brightness. So such like variable stars, exoplanetary transits, eclipsing binary stars, rotating asteroids, Gaia alerts, in particularly microlensing events and other transient events. So the first Gaia alerts object observed by us was in 2016. That was object well-known Gaia 16 AE microlensing event. So since then, we collaborate with Warsaw University. And in 2019, we got an opportunity to start our joint project, formalize our collaboration through DINA program, which is for joint researches between Poland and Lithuania. The first our project was started in 2019, and the title was Polish-Lithuanian Black Hole Hunt. And this project we finished in 2021. Then we had 3 years. We continued collaboration without any official project, but we still continued observations, finishing our started papers. And finally, we again applied for another project through DINA, which started in this year. The title is a little bit different. Polish-Lithuanian Black Hole Hunt, Harvest Time. The principal investigator from Polish side is still the same, Łukasz Wyrzykowski. From Lithuanian side, we have changed principal investigator from Marius Maskuliūnas to Edita Stonkutė, because this project is a little bit different, because we don't get any more such Gaia alerts, new Gaia alerts, but we still have what to do, how to try to search for black holes from analysis of archival data, also observing objects, doing spectroscopy for object classification, and so on. And of course, we will continue observations of other transient objects through BH-TOM. You already have seen this picture. This is our Molėtai Astronomical Observatory with 3 telescopes here. And here is our main building with rooms for observers and guests of observatory, with lecture rooms, kitchen, and the place for night excursions on the roof with small telescope. So everyone can apply for observations at this observatory. Observers can come to the site for observations, or they can ask for service observations. The large telescope is 1.65 meters, and we use it only for spectroscopy. The another one, the new one, 80-centimeter telescope in preparation for photometric observations. And the third one, 35-centimeter telescope with the main mirror of 50 centimeters, is Maksutov type telescope. This telescope was used mostly for Gaia alerts observations. This is the camera we use with this telescope, Apogee Alta U47. It is a little, has increased sensitivity in blue part. The field of view is 37.5 by 37.5 arc minutes. And we use with this instrument 2 sets of filters, Johnson-Cousins BVRI, or Vilnius photometric system, which is a middle width photometric system used for stellar classification. And now I will present you some statistical information about conditions of observations at Molėtai Astronomical Observatory, and also on what we have observed since our first Gaia alerts object. So I decided to get some histograms showing how many clear nights we have at Molėtai Observatory. So I use Meteostat package with the condition code. Clear sky we have when condition code is equal 0. That means that the sky is clear, or we still can have few small clouds. Also, we have to define what is the clear night. So I decided that clear night may be defined when we have 70% of the night with condition code 1. And also we have to define what is the night. In Lithuania, we have such problem that our latitude is quite high, 55% degrees to the north. And we don't have nights in June and July, but we still observe, we can observe bright objects. So I wanted to include those nights, actually twilights, into this statistic. So I defined that the night is between civil twilights. And here are two histograms. The upper one is for clear nights. So we can see that we have more clear nights between March and November. And bottom histogram shows it in hours, how many clear hours we have in each month. So when we look at the histogram for hours, we see slightly different picture. We see that winter months get better. We have more possibilities to observe than in upper histogram, but in June and July, we see that we have much less hours for observations comparing to spring and autumn. So the best months for observations at Molėtai Observatory are March and April, and then August and September. If we compare those histograms with our real observations, I included here only Gaia alerts and other transients. So we see that this histogram is more comparable with clear hours histogram. So we have less observations in June and July here. And here are very detailed histograms for separate months and years. And we can see, for example, here we have June. That number of clear nights vary dramatically from one year to another year. So sometimes we don't know what we can expect in particular months. And here are summarized all clear nights for separate years. I have to mention that we don't have full data from 2018 because they are available only from July of 2018. But we see that number of clear nights gradually decrease. 2023 was a little bit better. We don't know what will be 2025. It wasn't very good for observations, but we still have time. If October will be good, probably we will reach the level of 2024. And here a little bit more about observation statistic. So we started in 2016 here, very slowly with only several objects. And here we started our first joint project with Warsaw University. That was Dyna-1 project. And you see that the number of observed nights when Gaia alerts were observed, objects and frames increased dramatically. When we finished our first project, we still continued observations. We observed less number of nights, but number of frames were almost constant. And finally, in 2025, we increased the number of objects observed. Actually, after 2020, we got a little bit more picky because we wanted to observe only micro lenses. And now we understand that we should observe photometrically not only micro lenses, but also other transients. Yeah. Okay, this histogram shows that we observed through the week without weekends, all days of the week equally. And the object which was most have the largest number of frames observed was T Corona Borealis. And also on the top, you can see the length of the runs. 96 Gaia alerts were observed and 14 another transients. And here are examples of light curves. And our results are, I have counted 9 publications. 6 of them are on micro lenses. 2 of them are submitted or resubmitted, and I hope they will be accepted. Thank you.
Thank you very much. We have time for questions. So judging based on the statistics that you had, there is not much hope for clear nights this year, no? You're almost at the level of the average of the year.
Actually, I can show you one line I skipped here. Just a moment. Like here. So you see, according to meteorological statistics, in 2020, we had 55 clear nights. But actually, we observed for 120 nights. That means if we have gaps, for example, for 1 or 2 hours, we open the dome and observe. We have possibility to observe remotely, so it is easy. You sit at home, watch the weather and open. Because sometimes weather forecast is really different than you have.
But then you have some like alert, automatic alert that, okay, the weather is something, or is there someone sitting checking the webcam? No? All right. Any other question? If not, let's thank the speaker again. And now we move to Polish telescope in Chile. Yes, but it's Chile, no? So better nights than in Lithuania, I guess. So if Michał Zajmo. There we go. Paso. You can put it full screen. Okay. No, it's not presentation. Yeah, should work. Okay, so the stage is yours.
Okay, thank you. Okay, I'm Michał Zajmo, and I'm working in the observatory in the University of Zielona Góra, and I'm head of University of Zielona Góra Observatory, in short, UZO. It's easy to remember. It's not tequila, it's UZO. So for sure, all of you can remember this name easily. And today, together with Tomek, we'll talk to you a little bit about our observatory, our system, robotic optical monitoring system, and about the project that we are involved in. So the first question, as always, where is Zielona Góra? Zielona Góra is here, close to the border with Germany. We have small institute, 14 people in our institute is working for now. And this is the slide that I showed you 3 years ago when I was alone in our University of Zielona Góra Observatory, University of Zielona Góra Observatory team. but now our team is much larger. So I'm in that project together with Magdalena as data analyst, Tomasz Jachimek as a Python developer, Maciej Schneider as a spacecraft material specialist, Waldemar Grabowski as didactics and modern STEAM educational project coordinator. Our two great students, Agata as VHTOM project coordinator and Karolina as ExoClock project coordinator. And as you can see, there is also Agnieszka Gurgul. Her photo is shifted a bit to the right because in general, she works in a Toruń Observatory, but I know that her heart is with us and she is helping us with all of this SST project and is a project coordinator and data analyst. So a bit about our telescope. Our telescope consists 2 tubes on the one mount. So we have a 0.5 meter telescope together with 0.25 meter RASA telescopes. This telescope is located in Chile, but some specification about the telescope: the 0.5 meter corrected dark Kirchhoff as the main telescope that we are using for the astronomical project like deep sky observations, as galaxy observations, binaries observation, and so on. And 0.25 meter RASA telescope that we are using for this SST project for observing the objects on the Earth orbit. Both of them are on the L500 mount in ALTAS mode. And the telescope is located in Deep Sky Chile hosting that is located on the south of Atacama Desert, very close to Gemini South location. So it's a really nice place with the more than 320 clear nights per year. And now the telescope is still located in one of these shared roll-off observatories, but I hope next year we can move our telescope to our private roll-off observatory that is ready and is waiting for our telescopes. As you can see on the image, that there is a place for 3 telescopes because we have a plan to split our telescope, our Rotus telescope, to 2 separate telescopes. And also, as you can see on the image, there is a place for the one big telescope because finally, after 1 year fighting, this was not fight, this was war with our administration to sign the contract with ASA for the 0.8 meter Rishi-Krishan telescope equipped with a 2 Nasmith focus, CMOS camera, and we have a plan to also buy a low resolution spectrograph and polarimeter for the LSST follow-up and our SST project. So I hope in 12 months everything will be ready and we can use our new telescopes and our new observatory in our projects. And our main objectives, that's the most important, one of the most important, of course, project is the exoplanet transit timing. When we are involved in the ExoClock project that aimed at monitoring the times of exoplanetary transit for the future ESA mission Ariel. And also we are a part of the TESS mission follow-up as a sync limited photometry group. Here you can see a few results of our observations. The nice thing is that we already observed almost 200 transits and more than 70 of them are already analyzed and uploaded to the ExoClock and approved by ExoClock team. So you can see that even without the guiding, which is very important if you want to make a high precision photometry, we are able to reach the eclipses with depth like 4.5 millimagnitudes for stars around 12 magnitudes, or even transit with the depth like 2.7 millimagnitudes. The next results on the left, you can see results already uploaded by our student Karolina for star with the magnitudes more than 15, so it's quite faint object, and the eclipse with depth almost 23 millimagnitudes. And of course, important project for us, BH-TOM. Here you can see some results, some data uploaded already to the BH-TOM. The bad thing is that we have a lot of data for BH-TOM, but they are still in our archive because thanks to the great weather in Chile, the amount of data was too big to reduce and to calibrate them manually. So we had to wait for the automatization that is done now, and I hope we can upload all of the data from our archive to the system. I know it's not super fresh, as we can say that it's only fresh for 3 days. The data are fresh only for 3 days, like fish. But still, I hope the BH-TOM can get our data. Yeah. So on the left, you can see the data uploaded by Agata, and on the right, the data uploaded by Jan Andrzejewski. He was a high school student because, as Magda said, that we are also using BH-TOM as a project for high school students in our city. And the quite new thing about the BH-TOM data, because thanks to great feature of BH-TOM that it is possible to download all of the photometric data from BH-TOM, which photometric measurements of all of the stars in the field of view. We can do differential photometry using this data. And on the left side, this what you can see is an exoplanet transit with the depth of 20 millimagnitudes, and the transit is clearly visible. You can see that on the top, there is a photometry with the comparison star number 1, then number 2, and on the bottom you can see compare. But we have 20 minutes. Yeah. Yeah, and so as you can see, the transit is clearly visible, and you can use the BH-TOM data for exoplanet transit, and also, as you can see on the right side, you can use it, for example, for eclipsing binaries or anything, and it would be very useful for asteroids, and we are waiting for this feature for non-sidereal object photometry in BH-TOM. Another project that we are involved in is observations of asteroids for Adam Mickiewicz University in Poznań. In the animation, you can see one of the asteroids that we observed, I don't know, probably 2 years ago or something like that. And okay, and something a bit different than typical astronomical observations, because we are also involved in space surveillance and tracking project for the near-Earth object observations and space debris. So here you can see the animation that is showing our observations of the Olius satellite just before the orbitation of this object. This observation were made by Agnieszka Gurgul, but with our telescope. Thanks to the great plane wave mount, we are able to follow the even very fast objects on the orbit. So here you can see the next example of Falcon observations that we made at the end of the last year. And generally, we know very well how to do the astrometry of this kind of observations. So we know how to do the astrometry, how to find the position of the objects on the orbit. But the next step is to classify this kind of objects and to try to say something more about space debris, for example. And here you can see example of very simple analysis of the observation of the Falcon observations. On the bottom, you can see the flux that is coming from this kind of object, and this what is clearly visible, that you can see some periodic in the value in the flux from this object. So after very simple analysis, we can say that we can see that there is a periodic there is a primary signal about the 56 seconds because of the rotation of this kind of object, so which is typical for the large space debris or separated rocket components. This is just example of the simple analysis of the objects on the Earth orbits, but the next step is that we want to use the polarimeter and spectrometer in the future with our new 0.8 telescope to join together laboratory test of material degradation and the materials that we are using to build the satellites. And we want to join this laboratory test, how it works with the polarimetry and the spectrometry. And then we want to use this knowledge to classify objects on the Earth's orbits. Okay, and now we will smoothly jump to the poster talk, Tomek poster talk, exactly, yes. And you will get some more information about our robotic telescope system. Thank you.
Hi, Tomasz Jachimiak, Zielona Góra. Last year, at the previous Gaia meeting, we started implementing Observatory control system from LCO. It's an open source platform that we adapt to our needs. Observation can be planned by users manually or via API. We are also developing our own Python API client for OCS, and where observation requests are submitted, scheduler automatically calculates the observation plan for the night, and it takes into account priority and also observation windows. So the use of telescope is optimal. As you can see, there is two long observation from exoclock, and the gaps are filled with shorter BHOMs. For our telescope control system, we use Mina, which is controlled by our Python script through API. And the workflow operates with two loops. First, scheduler monitors observation portal for new observation requests and updates the plan. And second, telescope control system checks if the plan changed and executes observations. As observations process, we update statuses to keep everything in sync. When observations are done, they go to our pipeline orchestrated by Perfect, and the pipeline has several tasks like backup raw data at the observatory location, perform calibration, and finally send processed data to our computers in Zielona Góra. Nextcloud was our previous solution for sharing data with our users, but now we are migrating to Science Archive, a native OCS solution, which is more reliable and more safe, as the data access is synchronized with observation portal. And finally, researchers can obtain the data through the web interface or via the API, which which we can use to integrate with external services like BHTOM or ExoClock. And thanks to this implementation, we fully automated process from observation planning to data delivery, and now we are ready to expand our observatory with another telescopes. Thank you.
So we have two speakers, so twice that many questions. Nada.
Hi, I have a question. You said that at some point you mentioned that even without guiding, you can detect the dip. So that means you're not guiding at all. Your observations, at least right now, with the 0.5 meter, right, are not done with guiding.
No, yes, we don't have guiding for now. This is the system can keep the objects on the few pixels for, I don't know, more than 15 minutes, but still with the guiding, you can keep star, you can guide sub-pixel, so you can keep star exactly on the same pixels. So quality of the data is can be much better, yeah.
And for the 0.8, are you planning to, will you have guiding or will you do
For 0.8, yes, there will be a guiding, and I hope there will be also guiding for the 0.5, because there is a plan to move it to the to the wedge to make it equational mount, and then we'll also mount guiding, and yeah.
Yeah, and if I can ask another question, the spectrograph that you're hopefully gonna get, do you know already what's the limiting magnitude?
No, it's spectrometry is quite new field for us, so the first thing is just buy some spectrograph, and then we will see.
Okay, thank you.
And what resolution? I think I missed that.
The plan is for about 200. Yeah. Just to, classification of LSST alerts, for example. Yeah.
Okay. One more here.
Thank you. Agnieszka Gurkulum, Torin. I had to clarify because my supervisor is listening. My heart is with Torin, but my heart is big. I'm glad that you didn't say my heart is with tequila. I have a question to Tomek, basically, or maybe both of you, because you said that through the OCS, the data will be available to download from different archive and so on. So only data will be available, or are you going to also make available to schedule the observation on your system through the OCS?
Okay. Yes, of course, that's the system will be open for anybody who wants to use our telescopes. So if you are interested in, just let us know. We can register your account in our system, and then you can use API or a website to submit your requests for our telescope times.
Okay. Any other questions? We still have a few seconds left from the slot. Sorry for the confusion. That was on my side.
No.
So the very last question there.
I'm wondering, Nina has some plugin systems. What about OCS and Science Archive? Is it easy to extend functionality? Like, for example, add additional page to Science Archive or edit an UI? Is it easy or is it more complicated?
Yes, every part of the system has its own API, so we can grab the data on your own and show how you want to show it.
Okay, but for example, if I wanted to add additional button on a UI in Science Archive?
It's basically Django. If you know Django, you can do it by yourself.
Okay. I think that we can thank the speaker again and all the speakers of the session.
Yeah, and the last thing, here is our logo and QR code. That's, of course, It's linked to our website, and if you want to collect some stickers with our logo, it will be somewhere there.
Okay, before going to lunch, there is a last chance in next 2 minutes. If someone wants to come tomorrow, you need to provide us with the data in the next 2 minutes. Otherwise, you're not going. And I think that that's it, no, for this session. So thank you again. And Gabriela?
Sorry, I just want to remind you of this wonderful contest we're having to get these East bandanas. I know you were listening right now and you had no time for your phones, but over lunch, perhaps you friend the East on Facebook, Instagram, and LinkedIn, and you're gonna get this. And we have stickers too. Stickers for everybody. Stickers just because you're here. Stickers are cool. Thank you. Oh. Stickers, pretty. Thank you.
So you send it?
Yeah, I put it on Dropbox as you said. It's the same name, just with the.
Yeah. When? Today. When today? I'm not sure if it is already here. So that's
Saying that they are gonna share the entire
Poster.
okay?
Maybe it's the first.
Yeah. Okay, sure. I'm not sure, starting from the beginning. Oh, no, yeah. They will have to cut this. Good. But there is a version 2. So we are in this issue, no?
It's before.
Yeah, but we have the sorted by names. So it's version 2.
Maybe. But the name was.
We are renaming those.
You make, you name.
Not me, I know, but.
Okay, maybe I look only of this next info. Okay, it's the physics.
Yeah. Yeah. Sure. You are first?
Yeah.
Yes.
Okay, yeah.
Some help.
Yeah, but do you want?
English is-
No, not a problem. Now, you want to have it here for a whole lunch? No.
Thanks.
Are you going to sing? Sing a song? No?
Will always love you.
No, we need. So he wants to have a lot of here. He's the first. No, he's, yeah, but that's there is a change. It's good. No, it's not separate. It's
Okay. So you want to present from there?
No. We will be presenting from here, but I think.
Okay. Okay.
Can we do that a bit later? Because we yeah.
Can I need any program now? Can you open for? Oh wait, no, I'll put it on my.
But we still can link the program or the.
No, we'll show
or
first.
RSC.
Yeah. The last one. Okay, how are you?
So, okay. So let's get rid of everything that we got left. Hold on. Yep. Okay.
Then
Yes, no?
question, the question needs to download it to his computer and do the sharing.
Because it's
No, this is a Windows.
But do you have animation on the video? So, okay, we will look at
But we need to have the, or we need to say this share, the program is big. One more.
Very good. Nice. Yes, well, let's leave that. Why? Yeah, no word. Check. Yeah. Yeah, but yes. Animations. So we tested it here and they are from Focus Computer. And I need to confirm this with Focus, but I think this is the one. Yeah, she said that she is all set or already sent it. But she's there.
Thank you.
Let's take our seats and start on time. We have many small talks and some long talks, and we're gonna start with a short talk by Zbigniew Grabowski, and this session is on small telescopes and solar system. So we will have, the floor is yours, Zbigniew.
Yes. So, okay. Okay. Thank you. Hello, my name is Zbigniew Grabowski. I represent School Astronomical Observatory in Poland. It is 60 kilometers southwest from Krakow. We cooperate, our observatory is on the roof, the local school. We use the 40 centimeter Richard Chrétien telescopes. As well, we have smaller telescopes and photometry cameras. This allows us to combine education and real science. We cooperate with Polish universities and the East Foundation, for which we contribute data to BHTOM. Through this, our students join international time domain campaigns. Students complete the entire workflow from night planning through observation, data reduction, and finally creating live curves. The skills they learn include data analysis, statistics, teamwork, and report writing. Their activities become part of global research projects and public campaigns, such as monitoring the recursive nova T Corona Borealis, organizing the Perseid nights with the local community. We also are a community center. We offer astronomy lessons, open evenings, and organize the annual Cosmetic Summit conference, connecting schools, scientists, and astronomy popularizers. Our plans for the coming years include increasing participation in time-based campaigns, creating a remote observation schedule and a data repository, increasing the observatory's visibility in the local, educational, and scientific communities, organizing monthly COS meetings, workshops, and the annual Cosmetic Summit conference at an increasingly high level. I invite you to the next fourth Cosmetic Summit in May 2026. In summary, Bolencina is a small school observatory that inspires students and contributes real data to professional astronomy. We show young people the sky and let them take part in real discoveries. Thank you.
Thank you for the speaker. Let's have a minute for questions. Yes.
So I have only one comment. Paweł Zieliński from Toruń. Bolencina is great case that shows how to use small school observatory and how to use BHTOM together. So this is really good job, and congratulations for that.
Thank you very much.
Konstanze Zdecka, German Center for Astrophysics. I have a very practical question. How big is your team actually? How many people organize all of this?
We are,
And it's like time, I mean, who gets paid, who's volunteering, you know?
we have one really astronomer, Sebastian Krowski, who was next. Sebastian speak more about our observatory and science case, what we're doing. And he's the main man in our observatory. Of course, I'm not astronomy. I'm amateur, really amateur. But we have one man is in contract in observatory and free volunteer. That's can say free people have a little contract. No, it is not full work, full contract. Only some hours.
Yeah, let's
for people and 3 volunteers for time to time when it's big evening, Perseid nights or Perseid nights or so.
Yeah, let's thank the speaker again.
Thank you.
And move to the other talk by Sebastian Kurowski, who will tell about Little School, Big Sky.
Hello, everyone. And so I will continue on the story about this school observatory. I've been working there since already 2023, I started, I believe. And I will tell you not about the main activities in this observatory, but actually things that are happening after the main activities in the free time that usually in this kind of observatory is lost when there's nobody in the school. So as Byszek already said, Sułkowice-Bolęcina is a little village located in southern Poland. From the south is surrounded by the mountains. From the north, it's surrounded by a huge, heavily light-polluted area. We're just on the edge with Bortle class 4 sky, but actually it's not too bad. We can easily spot the Milky Way with good weather conditions, as you can see in the image on the right. This is an image taken by a camera that's installed on top of our telescope. So observatory is located on the rooftop. There is also observational terrace where we put smaller telescope for visual observations. And there's also an inflatable planetarium, but I will focus on the main telescope, which is under the dome. And as Byszek said, it's 40-centimeter RC telescope on a Skywatcher EQ8 mount. So basically, it's an amateur equipment, quite large for amateurs, but still amateur telescope, as you can just buy off the shelf. It's equipped with a CMOS camera, a filter wheel, off-axis guider, and a focuser, robotic focuser. So basically, I had all the things needed to have automatic and robotic observatory. So what I'll be talking about is I treat it as a kind of a testing facility to see what can be done nowadays with school telescopes and trying to make a full use of it and also squeeze some science into this observatory. It is amateur equipment. It has some limitations, but most of these limitations can be overcome by this fantastic software, which is Nina, free open source software, which is super powerful and enables us to control all the components of the observatory and also prepare observing scripts. So my first idea was to start remote observations and then even automatic observations. And here actually you can see part of the observing script, observing sequence, which takes care of the whole observation process for the whole night. So we just give the targets we want to observe, how many frames, in which filters, what exposure times, and it takes care of everything together with the weather stations. We have some upgrades because we're observing since 2023. I believe we started to do our scientific observations in July 2024, actually, sorry. And now we have new CMOS camera. We started with color camera, now it's a mono camera. slightly larger sensor, and also we have a new set of photometric filters thanks to the Jagiellonian University. Thank you, Staszek. And I want to emphasize that we are supported by many institutions. It's Zielona Góra Observatory, Suchora Observatory, University of Technology from Kraków. All of them give us some equipment that allows us to use this telescope more efficiently. So up to now, we uploaded around 10,000 points to BH-TOM. Last year, starting in July, we had 80 observing nights. This year, it is already 98 observing nights. So for Polish weather conditions, it's not too bad. And especially that we're using just the free time of a telescope. But here you have some examples of light curves. This is data only from our observatory for the T Corona Borealis. And the recent supernova, also in black, you have ZTF data. So the coverage is pretty good for this kind of targets. However, this automatization and remote control also give some other advantages to our other activities. For example, now we can use almost 100% of time, of the telescope time, which is, I think, quite unique for a school observatory. Also, we can very easily do remote observations from a classroom. So for example, during winter, when it's minus 15 degrees under the dome, we can sit in a warm classroom and kids can really easily point telescope to wherever they want, take some images. It's like 1 minute and they have already a nice picture. We can also do live streams of interesting astronomical events, for example, solar eclipse or lunar eclipse and so on. And sometimes you also catch some interesting phenomena using our cameras, one all-sky camera and one mounted on the telescope. Here you can see International Space Station with our Polish astronaut Sławomir Uznański. Our telescope actually was pointing in this direction, so just by accident, we also got it. Of course, telescope is all the time ready to observe because everything is configured. So we have a person, Łukasz Ciślak, our astrophotographer, who's taking fantastic images. And actually, this kind of images, even though they're not as beautiful as Hubble Space Telescope images, I think they have larger impact because they were taken in just next door observatory, right? And they also make this local community quite proud of this fact that they have this observatory there. Also, as this observing process is quite simple because of all this automatization, we also use it when there are some people visiting our observatory for public observation. We start from a terrace, having visual observations with smaller telescopes, and then we go under the dome and we show them advantages of a CCD camera or CMOS camera. So we observe the same objects pointing the telescope by taking super short exposure. So here we have an example of Orion Nebula, which is already visually impressive. But using a camera, you can see much more detail. And then we introduce filters. So for example, we can check how the hydrogen is located in this nebula. And here we have it. But there is also oxygen, which is slightly in different places. So here's the picture like 30 seconds later. And then we can have a look inside this nebula in infrared. And we have many, many stars hidden in this nebula. And this, usually there is a wow when we have these public observations that this is possible just in 15 seconds or 30 seconds, just standing next to the telescope, which is pointing towards this direction. And at the end, of course, we have to take color image of also. So there is another aspect that we can very quickly react to interesting astronomical events like Gaia spacecraft, which was turned towards Earth, so we can spot it with our telescope. So this wouldn't be possible if the telescope wouldn't be remotely controlled, because I was in Kraków at this time, but I noticed there is a small gap in the clouds. So I opened the dome, took some images, and you will see the clouds coming in a moment. So it was just time for several images, but it was enough to make this animation. And thanks to Łukasz, it was also noticed by ESA and Gaia mission. And I think it was the only observation from Poland, because the weather here was quite bad at this time, that was posted on their websites. So for such a small observatory, it's a really big deal, and we're super proud of it. And also science. This is the first scientific information about our observatory is just astronaut about supernova. But again, for such a small school observatory, it's a really big deal that somebody mentioned us in the scientific world on the International Astronomical Union websites. And of course, I have to mention the first paper mentioning our observatory. We're super happy that we could contribute to this light curve. And thank you for mentioning also the name of the observatory in the paper. This is also a big deal. It's nice to be a co-author, but seeing
even in Polish, it's written in Polish, Szkolne Obserwatorium Astronomiczne Bolęcina. This is fantastic. And we use it also to talk to people, to tell them about the observatory, that's in this small village. We can do this really cool things. We can do science here, which makes the local community proud. And local authorities more likely to give us some money to develop for the future. And there is another quite funny aspect about the local community. This is one of the screens controlling the telescope. And pay attention to this panel on the left. There are some buttons that allow us to control electric sockets. And one of them is signed as Kościół, which means a church. So next to our school is a church which is illuminated. And we have a button to switch off the lights of the church. So here's how it looks like. The church is bottom left, and then we switch it off, and there is slight difference. You can also notice it on a dome. But if the telescope is pointed to this direction under the dome, the effect is quite huge. So, and this is because we're doing cool stuff, we're doing science, so it's important that we have a dark sky, then it works. If you want to check what's happening at our observatory, what we're doing at the moment, you can visit this website. There you can see images from the cameras that are under the dome, the last image taken from the telescope, all sky image, and also below there are time-lapse videos created from these two cameras, the all sky camera and the one mounted under the telescope. So you can see what was happening last night at our observatory. And it's a fantastic diagnostic tool to check if everything works properly. And there are some new things implemented. So I wanted to do it even more automatic, so that I don't have to do anything and just press a button. If there's nobody in the school, the dome opens and takes observations. So we use this target scheduler plugin for Nina, which is a fantastic tool. You just give targets, amount of pictures you want to take, exposure times, image filters. And then it selects the targets, it's creating the schedule for observations and so on. It's great, but it's built for astrophotography. So after every night, you have to reset the sequences for every target manually, which was taking quite a lot of time. It was my daily morning routine for a long time. But it turns out that the target scheduler has this one file where it stores all the information about the targets. So we can modify it manually, or we can are using Python script. So I created a Python script, which is called Tequila. And this Python script uses API from BHTOM, downloading the list of targets every evening, then selecting the targets that are visible from our telescope by declination and glass magnitude. We observe brighter targets at 18 magnitude. And then is dividing into three priority lists, high, medium, and low, based on importance. We don't take priority for now, we take only importance parameter. So basically how it works, in the evening, the new list of targets is downloaded, then the target scheduler database is modified, and then we use Nina API to start the sequence. And then it's finished, and again in the evening, the new targets list is uploaded based on the measurements we already did, because we have this last magnitude parameter that we're checking. And again, the loop goes like this. And basically like this, the telescope was observing last month. I just started the script, forgot about it, and every clear night or gap in the clouds was used for these observations. And there is one more script which doesn't have such a nice name. It's ACME, from automatic calibration upload. So basically, it waits for a first scientific image to arrive on certain night. Then it's creating calibration master frames, and then calibrating all scientific images, dividing them into groups, and sending to BHTOM. And then waiting for the next image to arrive, calibrating, uploading. So basically, you have live feed of data in real time. It takes around 20 seconds from saving the image from the telescope and uploading to BHTOM. So basically, you have data live. And at the very end, I want to mention the thing that I said 2 years ago. I was telling how surprised I am how equipped are now the school telescopes. And here you have a map of observatories in Poland. The yellow one are educational, amateur, or private observatories. And many of them are equipped with this kind of telescopes. Almost all of them have go-to telescopes. So what a fantastic network of potential observers. And on these telescopes, most of the observing time is actually lost. Because if there is nobody at the school, in this observatory, it's just closed. But they're ready to be automatized and used in science. So I'd like to really encourage you to support these local observatories, to ask them if they need help, to suggest maybe to your students to ask for a job in this kind of places. For them, it will be a fantastic experience. And for this observatories, a fantastic possibility for the developing, and they would like to participate in this scientific project. They just don't know how. So at the end, I will leave you with this short video showing our observatory, and I'm happy to answer some questions if we have time. Thank you.
Thank you, Sebastian. Let's have a time for questions. Yes. Yes.
Fabian Schüssler, congratulations. I mean, this is great. And I just have a quick comment. You mentioned these Nina plugins, and it's great that you have the full circle now implemented there. Just in case you would run out of targets using Black Hole Tom, there's also a plugin for Nina reading the Astro Colibri API and database. So you can play with the app and set filters there and define which are the interesting events, and then the plugin would read from our API and database and fill the scheduler and things like that. And this has been provided by a motivated amateur astronomer from Switzerland, I guess, and then
Okay, that's great.
Thank you. Have a look now.
For now, we're filling the whole night with this high and medium priority targets. During the winter, maybe it will be different. It depends on the targets. It depends on the filters we set, how we divide them into these groups. So I will have a look at it. Thank you.
One more question, and then we will wrap up. Thank you for amazing talk. It's really nice to see the progress and what you can do, and the amount of the observatories even in Poland that can be automized. You said that you are presenting the work from night, but I'm curious if there are any students who are joining you to do some like scientific night observations, because this is the school observatory, or do you have any like classes with students from the school?
So yeah, I do have classes with students, but it's mostly primary school students, so we just take nice images using the telescope. But yeah, I'm planning to do this because, as I said, the telescope can be easily remotely controlled from whenever with internet access. So we're planning to go also to high schools, and there we can do some more interesting things like BH Tom observations. And also because now it looks in this automatic manner, we have also another idea to just allow people to submit the targets they want to observe, and we just add it to the queue, right? And so we want to be more open to local community, schools, teachers, and students. So I hope it will develop in the future.
So thank you, Stas. Sebastian, we will move to the next talk by Stasiak Zola on robotic telescopes and follow-up observations for Gaia alerts.
Forward. Yeah.
Sure. Thank you. I'm Stasiak Zola, Jagiellonian University in Kraków, Poland. You could see this title, but now I realize I was too optimistic. And the correct title should be the first one is okay, but the other part about the other telescope should be how to revive almost unusable telescope or forgotten telescope back into life. These are my collaborators, all guys working with me at the Jagiellonian University. All they helped me with the second part and keeping OAU J CD500 telescope working all the time. Previous talks give you some hint how it works, even in the conditions we have in Poland. And doing this to work in a robotic, autonomous way, make usage of all possible data. Currently, it is configured in such a way that even 20 minutes of clear weather could be used. The telescope will take some data and provide data for the users. The layout is short, so I will tell you about the current state and the improvement we have made since the last Gaia workshop. I try to be polite and do not tell what was the current state of the telescope we are going to revive or we actually revive.
because the state we saw when we did the work during the vacation time was really awful. But all succeeded, and now I can say that it's almost working in autonomous way. So the other one is OIUR and the name of the village where the telescope is. And please notice the first part of the name. This is the group name of the telescope, and I hope that next year I will have another one. Again, the first part will be OAUA, which is short for our university and observatory. So the current state was like that. This is OAUJ telescope. This is our CDK 500 telescope, which was commissioned in 2020, just when the COVID pandemic started. And I can tell that our students could observe during the entire pandemic. There was no break in training students' observations. It's fully robotic, and I chose to integrate it into the Skynet Robotic Telescope Network, which is run by people at UNC in USA. They provide, so you have just to configure the software on your side and then keep it running. And then you don't have to do anything else. Even you don't need a large disk for data because they store all the data. The current site is Jagiellonian University site on the outskirts of Krakow. We call it Fort Skała. It's an old post-Austrian fortification from 19th century. It's on the top of this fortification, and the site concerning light pollution is really awful. You will see in a second. We have airport on the north, and we have a freeway, highly lighted, on the west. Still, we can do some science, but it's our telescope and our side are mostly used for teaching. What we have is, the hardware is this. What's in green, this is new things. I'm not as happy as Michał is with the telescope, especially with the rotator, so I have to replace it with a new one. Unfortunately, the new version does not work with this telescope, so we have to replace it with the same model. The filter was also replaced from 7 position to 13 position. Now we have 2 systems of wideband filters, then VBI Stromgen filters, the only site with Skynet telescopes which has those filters. And currently we have installed Alta U47. Erika has presented this hardware, but we can also replace it with CMOS and also under EM-CCD. So that's why we have in BH-TRON 3 or 4 different names for the same telescope because of this equipment. The good news is that we finally are I hope, at the final stage of moving this telescope to some better site. And this is the site you can see. And this is a picture supposed to be secret because of the other people who are assembling the dome. And the dome will end up in this left tower, and it's already installed, ready for the telescope. Now we are assembling electronics, and I hope that before the end of the month, if we are lucky with the weather, the telescope will be a new site. Now a recall of what I told who attended conferences 2 years ago, 1 year ago. Skynet is a global network. It was created back in 2004. These are the core telescopes called prompt, and there is also telescopes, and we are one of them. Now about the new telescope. 2 years ago during the cosmetic meeting, yeah, thank you. I learned about this site. So then I visited the site and saw the equipment. I thought, why not to connect them to the network to make the telescope fully robotic, especially it was not used at all. It was like an item in a museum. People were coming, they were showing, oh, this is the telescope. Okay, fine. This is a telescope. But what not working? Then when I saw the equipment, I decided that we can try to make it working in an autonomous way. See its location. Sebastian forgot about this site on his presentation. At his slide, at this vicinity, there was no observatory. So there is another one. It's very close to the Ukrainian border. There is almost nothing around this observatory, just the road. And we can also control the lights of the road. Actually, people from this site. This is the equipment. Please note the dome. It's transparent during the daytime. When you have a very sensitive camera, it looks like that. The equipment is off the shelf. If you're interested in this, you can just take a look what the equipment is. This is now classical, CMOS camera. And last weekend, we had some filters replaced. Unfortunately, we couldn't replace with photometric filters, the astrometric filters. But now we have opaque and BG40 filters, which is actually a red blocker for the program, which I'm going to perform in about 1 week. What is software? As I said, is provided by the Skynet folks. We have Weatherman. This is the software which takes care of weather sensors. It communicates with cloud sensor and meteor station sensor. Then there is separate software for controlling the dome and the mount. They are provided by the manufacturer of those equipment. MaximDL takes care of observations, and the system integrator is, of course, if there is Skynet, there must be Terminator as well. So this is the core of this robotic system. Michel one day asked how make MaximDL stop taking observations because it's cloudy. The system takes care of that. If you got a signal, it's cloudy, it sends signal to Terminator and it stops observation, closes the dome. And then it can open the dome as well. This is the proof. We have already connected it to the Skynet. So you can see OAUS in Polish Tymce, name of the village. So it's online, weather was bad, but it's locked. It's still in the testing mode, not in a production mode, but in the testing stage. This is the software which runs on the computer. A regular user never sees this. So this is only for system administrators. And this is also the proof that the site of the first light, these are stars. This is not T Corona Borealis, but I didn't know that everyone should present this one. Actually, I have taken with this telescope. And this is the sky. And actually, this is the summary in this way. So we're going to move from site which has sky like shown by camera on the top left to something which is at the bottom left, and the two dots on the map show how we're going to move by about 50 kilometers south of Kraków. Tymce is on the top right, and we can control the light with a very low. These are the lights from the street. And of course, sometimes you have natural pollution. We've already seen how atmosphere looks in spectroscopy when you have, this is actually an aurora taken some time ago. This was 1 year ago, and I took students for just one night to Mount Suhora, and we had this. Okay. So I skipped this. I was going to tell something to Łukasz, but I will tell him tomorrow. Thank you very much.
Thank you. Let's have a time for questions. Yes, please.
Hi, Nadek at ING. I have a question about the I believe it was called it's called Weatherman for the weather sensors.
Yep.
Can you comment on it? How does it work and what type of sensors they are? Like you know.
It's compatible with several weather stations. Speaking like that, every 5 seconds, it checks the signal for the weather station. There are special thresholds you can set up, configure them. And if you exceed the threshold, it sends the signal to terminator. It's cloudy or too humid or too windy. These are the three parameters which are taken by this sensor. And then there is cloud sensor, also with the threshold. Also sends signal every 5 seconds to the weatherman reads that. So it goes too high, and it sends a command to terminator observation and close down.
Does it also distinguishes between thin clouds or you know patches of clouds? It's not.
I'm afraid that it doesn't have. So this AAG sensor is not good enough, I would say, to distinguish it. If you configure it in a proper way, usually there's also some kind of margin, and this is usually place where the thin clouds are. I mean, thin cirrus clouds are. Then you can decide what. I mean, a person could decide. Observation should not go wrong when the conditions are like this.
Thank you. Yeah, really good.
One more quick question, yes, please.
It's actually on the same topic as that one. So I couldn't understand, you have these sensors locally too, right? Like it's right there. Can you talk a little bit about the sensors? Are they also some off-the-shelf standard things that and then the software comes with them, or were those two different pieces that you had to develop, integrate, whatever? Some comments on that. Thank you.
Actually, part of this weather station you can see on the right. This is this device checking how strong the wind is. Well, communication is via the protocols which are provided by the sensors. One is connected via USB, and the other one to the COM port. And weatherman understands the signals which are transferred from those sensors. So this is simple, but you know, observer never works with this. So for them, it's just like a black box. There are our students over there who are doing many observations with our telescope, and all they do is to submit a job with a browser and upload the data already calibrated by the Skynet pipeline, and then upload it to the BH-DOM.
Okay, let's thank the speaker again. And next presentation is by Vytautas Čepas on a new telescope in Molėtai Astronomical Observatory.
Good afternoon. I'll speak about our new telescope that is less than a year is installed in our Molėtai Observatory. Yeah. This is Molėtai Observatory site, you know. It contains 3 telescopes my colleagues have spoken about. two of them, and the third telescope is new one. It's 80 centimeters telescope I'll talk about. It is equipped with 4K CCD camera, a filter wheel disc, and Bessel BVRA filters, Sloan filters, and some specific filters. Yeah. Here how it looks. Our new telescope. It is installed in this dome. And my colleagues think we don't have technicians in our observatory, so everything we have to do ourselves. Yeah, my colleague Justas and Marius are installing webcam on the telescope, and here's the picture of a telescope, how it looks now. You see CCD camera, Princeton instruments installed, and it's also CCD camera has a chiller, and it's cooled down to minus 90 degrees. Yeah. The telescope, we had the opportunity to buy these telescopes thanks to structural funds money. We participated in a project that was the name of a project, update of S3 in the infrastructure to create good scientific infrastructure for astronomical community of Lithuania. So as you see, telescope is 80 centimeters wide. Payload capacity up to 300 kilograms. Good tracking accuracy. Telescope was made in Austria, so the technicians came here to Molete Observatory and installed the telescope, and we also provided material how to operate that telescope and trained our observers. The telescope is equipped with quite good CCD instrument, Teledyne Sophia camera, 4,000 and 4,000 pixel format, cooled, as I said, up to minus 90 degrees with liquid chiller, low noise. As the manufacturer of camera says, it's very good for deep sky imaging, wide fields surveys, exoplanet characterization. And as I said, we are only starting our work with this camera, and I just want to share with you some scientific images. Field of views, almost 40 arc minutes. And here, there are some exposures, and about 10 targets are in black hash storm now, some exposures. So we are starting introducing this telescope to Molete telescopes family, and we want that this telescope will be very productive, and it would be very good, how to say, window for further collaboration. Yeah. And thank you for your attention. Yeah.
Thank you, Vitas, for sparing time for questions. Do we have questions for Vitas? Yes, Milena.
Thank you very much. I was wondering if someone applies for time or wants to use your telescope time, then do you provide the raw data or you reduce it somehow? Is it possible to use some of your reduction procedures that you use?
We use usually our standard procedures, but if you want to observe yourself, you could observe. You ask for observing time, and there is a special commission. And if you pass, you could observe, and it's not a robotic telescope, but you could use it remotely. Yeah. If it's enough equipment, we have 10 filters.
I can add as well that this is a new instrument. We don't have yet procedures on the data reduction, but with the reduction for sure.
But IRF does, if we talk about photometry, you could always use, for example, IRF package, but it's by economy for astronomers.
Łukasz Wyżykowski here. So just to comment on this, so in terms of photometry, I've just checked that this very telescope has already contributed more than 200 images.
The best tool for photometry, you just put in black hash tom and don't care about photometry.
Exactly, that's the thing. That's
yeah,
the thing.
well,
So
you do.
You ask for observations, you process the data for BH-TOM, and it's already in the system.
Yeah.
So I wanted to emphasize the speed and the quality of the data of this new telescope.
Yeah. So we are installing, and I think after a few or 4 months, we'll have results.
Thank you. If there is no more question, we can move to the next speaker. Thank you, Vitas.
Thank you for that.
So the next presentation is by Nicholas Slam. It will be a short one.
So hello to my short presentation. It's about the Observatory Lustbühl in Graz in Austria and its BMK telescope. My name is Nicholas Lampel. I'm from the Institute of Communication Networks and Satellite Communications from the Technical University of Graz. So at our observatory, we have 2 telescopes. One is a 50-centimeter ASA telescope, which has a focal ratio of f/9. It is mainly used for spectroscopy because we have a spectrograph there, and also 2 mono cameras. And the new telescope, which I'm talking about today, is the BMK. It is a ballistic measurement chamber produced by Zeiss in the 70s. And it was previously used to observe satellites and track them using photoplates, and is now repurposed to be used in scientific studies. So the main difference between those 2 telescopes is the possible field of view, which you can see here. To put that into perspective, on that image here, you can see the small green rectangle, which is the field of view of the ASA telescope. And the red rectangle you can see there will be the possible field of view of the BMK when it's fully operational. So for the refurbishment process, we started with just a mechanical setup and had to add all the electrical components. And we focused on using open source projects to keep it cheap. So the computer runs new, connects to the dome, which was connected with switches, and are controlled via a dome controller using ASCII. We also used another open source with Open Astrotech to use for the motor control, for the mount, and also use the focus motor of the camera, and also the camera and the filter is connected to the computer. So all the connections are done via ASCII. And because of the use of open source projects, we're able to keep the entire refurbishment process just under €1,000. So what will be the new capabilities be? We can now do and photometry at the same time. Also, because of the larger field of view, we will be able to have more reference stars, for example, when we observe variable stars, and we can also observe the same field of view with the telescope and then compare the two results. And it is also to add the BMK telescope to the BHD network when it's fully operational, which will be around mid-December.
Thank you, Nicholas, for your presentations. We have a time for questions. Yes, please.
So what was happening until this refurbishment? Was it still observing the satellites? Was there a long downtime? Were students using it? What's been going on in the last few years?
I mean, so it was built in the 70s, so it was then used with the photo plates, but when they got out of date and the technology in laser ranging evolved, it was then reactivated in the mid-2000s for a master thesis and was then again 15 years not in use. And then I came and got the opportunity to now refurbish it. And I mean, it's a very good telescope because of the photo plates which it was used. It shows almost no chromatic aberrations because you can't correct them on the photo plates, so you had to correct them in the optics. So the telescope consists of 10 lenses and has a weight of just 200 kilograms just of glass. So that's quite an impressive instrument.
More questions? Yes, please.
So amazing work. How many nights you have roughly? Good nights, clear nights?
So in average, we have around 120 to 130 nights we can observe. And we try to move to more robotic operations. So this telescope then will already be remotely controllable, so you don't have to be at the observatory. We also want to repurpose the main telescope, the other one, to do that, and maybe then move to robotic telescopic like systems that were introduced before, so we can use the full extent of the nights.
Thank you.
That's very great. Are there any preferences for kind of targets or activities? What you what you have in mind to do with it?
I'm just an amateur astronomer, so I'm not a professional astronomer. I will leave the research to the researchers. We will operate the system. I mean, it will also be used for student training. So we have a lot of students who do practical sessions with the main telescope, and now they have a second one. For me, I would really like to do some nice images and, for example, of large star clusters, which will be now possible because with the other telescope, you have such a narrow field of view. So it will be the thing I would want to do with it.
Thank you. More questions? If not, let's thank Nicholas again. And we have last talk, coffee break by Andrea Gomboc on research and teaching with Slovenia Go Chile telescope.
My apologies. I thought that was one more before me. Sorry. Okay, so I'm going to present briefly Go Chile project, which is a Slovenian relatively young project started as an idea in 2019, and we were on the sky in 2021. We would be on the sky in 2020 if there was no COVID pandemic. So Go Chile is basically two small telescopes, 40 centimeter reflector and piggyback 27 centimeter refractor. They're both equipped with cameras and different filter wheels. So, the name Go Chile comes from the fact, so this is a collaboration of amateur astronomer Matej Michelčič and, okay, thank you. and the University of Nova Gorica. So this is why we have Go in the name, and Chile reveals the location of the telescope. So this is mainly pedagogical telescope. So this movie, which is about to play, should start in our location, School of Science in Slovenia, from where our students remotely connect to the telescope and use it. So this has an advantage. They can use it also in the morning when it's still dark in Chile. And this is the observatory, El Sauce Observatory, owned by company Obstech, where the conditions are very good. And it's just 25 kilometers from the Vera Rubin Observatory, where we also participate. So we have more than 300 clear nights per year. And the data from Go Chile and from Rubin come eventually to us or to everywhere else in the world. So as we are interested in astrophysical transients in our research, based mainly with Vera Rubin Observatory and other telescopes, this is also what we are using occasionally, this Go Chile telescope for astrophysical transients, for example, supernovae, gravitational microlensing. And you see one such example in this picture. And also our students are using Go Chile. This is the main purpose of this telescope for different research projects that they do, from exoplanet transits to asteroid rotation and many others. Since we had some problems lately with the quality of images, with the tracking, we are planning to upgrade the mount in the early 2026. With this forks, with the mount which has adjustable forks, which means that eventually if we would have more money to buy a bigger telescope, we could also install up to 80 centimeter telescope in this place. We also give, since we have a lot of time available, we give a lot of time also to high school students. They can do many different projects, whatever they want, from astrophotography to some mini research projects. We had, for example, in these 4 years, I think our projects won twice the national competition in research projects in Slovenia in the field of physics, general, not just astronomy. So we're very proud of that. We also organized summer schools for high school students. Here is the 4th edition, which was international this year, and we had 20 students from 6 different countries. So we are recently also opened the archive. So all the images that we have taken are available in this archive. It is like open science or citizen science. So it's available for everyone to access. And since we are at I could show you some nice pictures, but I decided to show you just these 2, since we are in the Gaia meeting. So you see the Gaia satellite, as also some previous speakers showed. And also we have here in the upper image or movie, we have James Webb Space Telescope speeding towards the L2 shortly after it was launched. So I think this is nice way of showing also what little projects we can do with this telescope for fun. And I will leave you with a short film that our students of Academy of Arts made about this. Other students of physics and astrophysics who are using the Go Chile telescope. So I would ask for sound if it's possible, Lukasz, but if not. But if you have any questions, you are welcome to ask. Maybe some of you know Martina. She was in Gaia Alerts meeting last year in Crete. Any questions?
Thank you, Andrea. Let's have a couple questions. Before colleagues are thinking, can I have a question myself? Can we track how many of those students actually can choose astronomy, astrophysics for their career, and they have those nice opportunities?
There are some that we know that they chose that, but then there are some that just got interested in astronomy and they will keep it as a hobby.
Yes, please.
So you mentioned, well, Nadia from University of Lagos, Barcelona, sorry. You mentioned that the school was open internationally for high school students. So how the process works or when you have to apply, because we may have some motivated students that will be very interested in
Yeah,
that.
so we opened the applications in spring. We just, this year when we decided to go international, we just spread the news in the neighboring countries. So we had students from Croatia, Serbia, Bosnia, Hungary. So the process is basically they have to apply. And the thing is that we don't select based on the, I don't know, the achievements, but motivation. So they have to write a short motivation, why they want to attend, what they want to gain out of that, and then we select based on that. Yeah, I will send you the link next year.
Great, thank you.
So we have two questions. One, and let's have you first and then colleague afterwards.
So you are based in Slovenia, the telescope is in Chile. You mentioned there were some hardware issues. How does it work when something goes wrong at the observatory? Is there somebody there at the site to troubleshoot?
Yes, so actually so far none of us have ever been to this observatory in Chile, and we've been using it for 4 years. The idea now is that with the new mount, this Matej Michelčić, this amateur astronomer who is basically the mastermind behind the technology of this, will go there and install it himself. But otherwise, previously we agreed with the personnel at the observatory that they helped to install everything. And if there is any particular issue, they are there to help and do that.
I have short comment about Slovenian students. During the International Astronomical Olympiad, 5 members of Slovenia reached the gold, 1 silver, and 1 bronze medal. Much more than Poland. You can compare the countries. Okay. Thank you.
I know them all, and not to brag, but last year Slovenian student was absolute winner of the Olympiad for the 2nd time. So I'm just saying.
I think that's great. Great job you're doing in Slovenia. Thank you again. And now coffee break, and we'll come back 3:15, right?
I had it here. This is PowerPoint.
Thank you.
you can then you have a very long side, and they get what of the rest of the data for the amount of something important, during the observation. And now, if you want to make that, you have to ask how to cover our doing wrong. And yeah, doing the night. To make that. No problem with that. Fine.
Ah. Wait, no.
Okay, yes, oh, yeah, so name of your record, we can put the same name as yeah. For example, yeah, it's gonna get
the first of yours and
I think jest tam szkoła i najpierw nas grupę tej grali, że było widać. Zrób nam zdjęcie.
Foteczką.
Bo wiesz, do szkoły chcemy, nie? Tak, żeby było widać Gaia.
I think so, yes. We have all the talks, at least I thought that I was told that we have all the talks. We have guests. Zapraszam.
A nie, wiesz co, ty, a z tobą też astronomem. Trochę tak jak on. Kanapka, dobra.
Super.
Videos?
Yes, I've more information about research.
Jak macie kopa, ja mam dzień dyskutowany i nie zostałam, bo słuchajmy się waszą odpowiedź. Ale co robisz? Dawajcie, stań z nimi. Kanapka z Basi teraz, bo Basia też jest... Tak. No i na Insta. Dobra. To coś jeszcze? Tak nie rozmawiacie, ty współpracujecie. No tak, to dużo się dzieje.
Bardzo dziękuję.
Tak? Posłucham ciebie i potem wyjdziemy po angielsku.
See the chair.
The chair?
Next slide. I adjust the microphone?
Yes, sure.
Okay, one. Wait, Padek? Czekaj chwilę.
No, I deleted and check again. No, this one. That was the first one, so. Not really. Can you check that?
That's okay.
It's the
Yeah, I just
latest one?
because I added some after sheet.
Yeah, but you should. This is it?
Yeah, this is
Okay.
it. That's fine.
So let's take our seats again. We will continue with a short talk now. Take your seats, Sharunas. Milena, Sharunas. So Barbara Hanzilik, sorry if I pronounce your last name incorrectly, astronomy in the city.
Yeah. Hello, I'm Barbara, and together with Waldek, we will represent the Silesian Planetarium Observatory. The Silesian Planetarium is located in the south of Poland in a huge urban area. It's the same urban area that Sebastian showed that it's making light pollution in the north of Bolęcina. And actually, the planetarium is located in the middle of it. You can see the pin there.
So the sky is not great. The planetarium consists, of course, of the planetarium in the big dome, the observatory in the smaller dome, and also the science park in the rest of the building. This year marks the 70th anniversary of this institution, and 3 years ago it was reopened after a major renovation, during which all of the components were renovated. In the observatory for the last more than 60 years, the heart of the observatory was a big 30-centimeter refractor, and it was replaced by the 70-centimeter CDK by plane wave, a much newer telescope. And it has very useful dual Nasmyth focus, which allows to make both public observations in the one focus, and the other one we have is equipped with the science grade camera, and we don't have to dismount the camera to make public observations. The main goal of this institution is, of course, outreach. The science topics are astronomy, seismology, and meteorology. And last year was the first year in which the new observatory was opened and used by the public. It is opened mostly during the weekends and during the days, but we have some special nights that we can use the telescope with public also during the night. During the day, we show some of the brighter planets and stars. During the night, of course, we have more options for the objects. And thanks to some astronomers, namely Waldek Ogłoza, we can use this telescope also for science. This year alone, we had almost 90 observing nights, and majority of the objects are asteroid light curves. Maybe it's 80% of the observations. The rest is occultations by asteroids, and of course, BH10 targets. Right now we have around 2,400 entries. And of course, some other project that people want to observe, and the target is bright enough to be observed in such a light polluted area. And something to celebrate maybe with tequila later. The observations from our observatory were used in 2 science publications by now, and I hope it will be more. This telescope is next of the educational telescopes that can be used also in science, and I hope many more to come. Thank you very much.
Thank you, Barbara. Let's have a time for questions. Yes.
For the science observations, are you guys fully automated, robotic? Like, what's your mode for the science?
It's remote. We can use it remotely after the working hours of the planetarium, but it's not fully automated yet.
More question? Yes, please.
Hey, Fraser Gillen, NCBJ. So I was wondering, for your observations that you're putting into BH-TOM, I assume it's the non-asteroids that you're putting into BH-TOM?
Yes.
Right.
Most.
Thanks.
Okay, I don't see any more hands. Let's thank Barbara again. And next presentation is by Anita Heward, Europlanet.
Right. Thank you, everybody. Thank you, Edita. My name's Anita Heward, and I am the Vice President of Europlanet. And I'm here to talk to you today about the Europlanet Telescope Network. So I'm just going to give you a brief introduction about Europlanet itself to kind of put into context the telescope network and why we're doing that. So Europlanet's a worldwide community to support the study of our solar system and exoplanets as well. It's a non-profit association based in Brussels as of the past 2 or 3 years, and it's a membership organisation. So we have individual members and we have organisational members, and I'll talk about that a little bit later. The services it provides have been developed over 20 years with funding from the European Commission and the planetary community. And this is sort of how we've come about. We came out of the Cassini-Huygens mission. The planetary community historically was very fractured in Europe, with people in many different countries doing planetary research, but not really knowing each other. And so the first big mission, pan-European mission, Cassini-Huygens to Saturn, where there was the Huygens probe led by ESA, but also a lot of European involvement in the Cassini orbiter, was really the first time that the European community kind of woke up and realized just how much activity there was going on. So they put together an integration grant from the European Commission that they were successful with under FP6 for 2 million euros, and then went on to form a research infrastructure that provided facilities and field sites to the community. And that's been growing over the past couple of decades to the latest project, Europlanet 2024 RI, which had 56 beneficiaries and ran from 2020 to 2024, offering access to field sites and laboratories, to virtual access to virtual observatories on planetary data, to coordinating activities for the community. And so we got to the end of our 2024 grant, and then, well, actually, we didn't get to the end of it. We planned. So for the last decade, we've been thinking about how we can support this community. And as you can see from this map, it's not just a European thing. We have field sites, we have laboratories from partners all over the globe. And the aim of this is really to join up the community, to provide connections, cross-boundary, cross-border connections between researchers in different countries, in different continents, and in ensuring that our very, very interdisciplinary community has access to the facilities, the tools, the resources, the expertise that it needs. So, as I say, in the most recent project, we provided access to laboratories and field sites. We also provided experts exchanges, so enabling researchers to go and spend some time with people in other facilities and other laboratories to learn, to share best practice. We had a virtual observatory for planetary data. We developed space weather tools, a mapping service, a planetary mapping service, machine learning tools for planetary science, and a global network of telescopes and support services for the users. And that's really what I'm here to talk about today. So why does planetary science need a telescope network? Well, ground-based observations play a big role in the study of planets and exoplanets. We've been hearing a lot about that over the past few days, and we'll hear a bit more about it this afternoon as well. Stars, asteroids, comets, related objects, and all planetary missions need observations to support them before they go, to understand better their targets, and also to follow up observations once they're in orbit. So, for instance, if you see a storm develop on Saturn, then it's also useful to be with a mission at Saturn. It's also useful to be able to deploy amateur users and small telescopes around the world to follow up those observations. And small and medium-sized telescopes are very useful for a variety of fast reaction and long-term projects, and can really produce first-rate science. So this is something we wanted to do for a long time, and we finally got the funding within the last project to do it in 2020 with the Europlanet 2024 research infrastructure. And we had within that a budget of about 500,000 over 4.5 years, which supported access to telescopes, observational alerts in support of planetary campaigns and missions, and also to run some training programs for early careers and for amateur astronomers. The telescope network, by the end, involved, I think, 17 organizations and about 40 telescope facilities in total. And we collaborated with lots of different other services ongoing, including Gaia for asteroid alerts, and developed an alert system for other planetary related campaigns. We collaborated with PVL, the Planetary Virtual Observatory and Laboratory, who also is a repository for data, for planetary data from the professional and for the amateur community, and also sends out alerts for things like storms on Jupiter, Saturn ring crossings, and various other things. You've heard a number of presentations about exoclock, and exoclock users apply for time on the Europlanet Telescope Network. And we also collaborated with them on several workshops over the project. And in total, we organised 23 workshops in summer schools, attended by over 1,300 participants. This was on a range of topics: ground-based support for missions, fireball detection, asteroid research, general observations using big telescopes for the amateur community. And through the telescope network, we had a series of calls. We had a rolling call, and then we had time-specific calls. And these supported, over the course of the 4.5 years, 44 projects and 256.5 observation nights at the facilities that were participating, including here in Tenerife, but also Mayatai Observatory, which again you've heard a lot about, and observatories all around the world. It was a difficult time in that our project coincided with COVID. We started almost exactly the same time as COVID. But nonetheless, although we possibly didn't do it in the same way as we thought we were going to do originally, and there was less actually going to facilities to do the observations there, in any case, remote observations over that time period were becoming more and more common. As you can see from the some stats from the evaluation, we supported a range of people at career stages, over a range of career stages, including many early careers, also many amateur astronomers. And it was one of the most successful parts of the Europlanet project overall in terms of supporting people from underrepresented countries within Europe. 26 papers have come out of the projects, the projects that were funded through the Access Programme for the Telescope Network. Most of those are on planetary science, but some of them weren't. Some of them were beyond that. We also supported a programme for Ukrainian researchers to do observations within Ukraine and to also visit facilities outside Ukraine if they were able to travel. I'm just going to say something briefly about evaluation of Europlanet overall, because I think this is relevant to the telescope network as well as to the wider project, that there are significant benefits of these projects, these access mobility projects, beyond just publication. So great science does come out, but in terms of the TA programme, our transnational access programme, where people went and visited facilities, I think the same is true of the telescopes as well, that over 90% resulted in future research activities. And all kinds of other things came out of those as well, like forming consortia for future bids, co-funding of doctoral studentships, and just generally ongoing partnerships. And this has been particularly important in building partnerships beyond Europe with partners in Africa, in South America, and so on. The impact's particularly strong for early career participants. Of our visitors, over 50% were early careers. And this provided them with opportunities that were not otherwise accessible to them. And those impacts are then amplified into their future as they go on through their career, building on those collaborations that started through the visits, through the contacts made through the project. Networking support was very important for early careers and researchers, mentoring, expert exchanges, training, all very highly valued, very good feedback. And this was particularly impactful over the past few years during the pandemic and the time coming out of that. Amateurs play an important role in planetary science and a rich source of data, so this is particularly relevant to the telescope network. And that coordinated program, not just the access to the facilities, but also the alerts, the coordinated campaigns, training, dissemination workshops wouldn't otherwise necessarily be available to them. And investment through facility upgrades that were possible through the EC funding were also important in building capacity, particularly in underrepresented countries. And so all of this, the sort of takeaway messages, collaboration and networking are really important to helping to deliver world-class research and bringing people together, as we've got here this week in this room, and also, you know, particularly in going and spending time during a research visit helps to refine ideas and overall leads to better science. So where we are at the moment, Europlanet is now established as a non-profit association to promote the advancement of planetary science. We fund that through memberships. We have organizational members and we have individual members, and those subscriptions, as well as income from our big annual meeting, which attracts about 1,200 people each year, and exhibition and sponsorship around that, enables us now to run a small scale program similar to that which we've been doing with the European funding over the past few years. So we've run transnational access, we've run our winter school, our geological mapping activities, and we will continue to run expert exchanges, mentoring, communications, and so on. This telescope network at the moment has a list of the telescopes that are willing to offer time, are interested in collaboration. So there are details of the contacts, the facilities that are offered. All the details that you need are in this table. Yeah, but it's currently in passive mode where facilities are listed, but there's no active coordination in terms of calls, in terms of peer review, in terms of support, training, monitoring of activities. As well, we have a lot of overlap with a lot of the things that you've been hearing about this week. So we have a lot of overlap. Our telescope network is similar to those listed in EAST East, in ACME, in Opticon Alliance. And we know from the European Commission there aren't going to be calls in the foreseeable future. So the reason that I'm really here for this meeting is to talk about how we can potentially pool activities to operate one telescope network with a common platform, peer-reviewed calls, support for the community. That potentially could be funded through a membership model for facility members and user members. How exactly it's going to work, I don't really know. But what I would like to do is ask you in this room today, tomorrow, come and talk to me, tell me what you need, what you would want, what you would prioritize, and what you might be able to offer. So I'm here this afternoon, I'm here tomorrow, or you can follow up by email. So thank you.
Thank you, Anita. Let's have a question for Anita.
Hi, Łukasz Żyżkowski, I was first. Just a quick comment. So the list of telescopes you showed, so we know at least half of them. We've been cooperating with them through BHSOM already. So I think it's more than natural to combine the resources.
Yes.
Hi, Simon Hodgkin, Cambridge University. You mentioned peer review here, and I wondered about the context under which you're describing peer review. For example, with BHTOM, as far as I'm aware, we have no peer review process. So are you talking about the use of the resources being peer reviewed by a committee?
Yeah, so what we did do within Europlanet, and I understand from Jerry is same within Opticon, is that people would apply for time through, we would have calls, people would apply for time, there would be a panel that would review them, rank them, and the highest ranked ones would be offered the time. So there is a level of, you know, scientific excellence that's maintained through that. And I think this is one of the things where at the moment where we've just kind of got this passive mode is something that we can't control at the moment. We don't have any knowledge or information about, but this is why it's important to have calls, to go back to having calls and pooling resources as much as we can to enable that to happen.
Okay, thank you. Thanks very much.
More question? If not, let's thank Anita, and Anita is around. We will continue with the Fraser Gillen and VH Tom and Solar System.
Yep.
All right. Hi, everyone. So my name is Fraser Gillen. I'm a postdoc at NCBJ, working with Łukasz Wyrzykowski. And I'm going to come and talk to you today about BH Tom, but from a slightly different angle. So I'll talk about it from the side of a solar system scientist, where my background is primarily in comet and asteroid photometry. So the current surveys that we have for solar system are primarily, Atlas, CTF, Catalina, Pan-STARRS, and in future, of course, we'll have LSST, where they all have their different strengths. For example, Atlas and ZTF have a wide field of view on the sky, but maybe don't go so deep. Something like Pan-STARRS goes a lot deeper, but then has a narrower field of view. But as we've heard throughout this week, it's also important to note that these surveys have their limitations as well. Whereas they're going to, they may only observe the same field of view on the sky every few days. And if you then consider filters, it may be even a week before you get the same visit and the same filter. And then it's also important to know if you're only using surveys for time domain astronomy, it's normally not possible to do follow-up observations or target opportunity observations because these surveys are on fixed schedules. So this is obviously where BH Tom comes in. And you've probably seen this to death, but I'll just go over it very briefly here. So there's 130 telescopes worldwide covering northern and southern hemisphere. But the point is that there's going to be someone somewhere at some time that will probably have some clear skies and will be able to get some kind of data. The observers can contribute, hundreds of observations per night on a target if they want, or one observation every couple of nights. But the point is, if everyone contributes 1 or 2 data points a month, say, if everyone does that, you eventually will get a nice time series curve of whatever object you're looking at. And then, of course, everything is calibrated and standardized in BH Tom automatically, and it also queries the archival data as well. So this is quite a wordy slide, but just bear with me here. So to adapt BH Tom for the solar system, we need to make some clear additions or changes. So number one, solar system objects are non-sidereal, i.e. they move relative to the fixed background stars. So currently, if you were to look at a solar system object, you would have to create a new target for every single observation, which is not practical. So we need to, first we need to link all of these observations. So it'll be a case of querying something like Minor Planet Center or JPL Horizons to get the ephemeris of the object. We can then see its position on the sky at a given time, and then link these all into one target and get the one light curve. And then we'll do the same process for archival queries as well. The next addition we need to do is that comets and asteroids can have multiple names or multiple designations. So I've given the example here. There's the Centaur Chiron. When it was initially discovered, it got an asteroid class classification. It wasn't active. It had no coma, no tail. So it got the designation 2060 Chiron. A couple of years later, it then became active. It showed a coma and a tail on the sky and got a new designation 95P Chiron. These are the exact same object. So you want to be able to, again, link these in BH Tom so you don't have two separate targets here. And then the third point is for the community observations, when we ask and request observations for solar system objects, we need to be able to communicate clearly to the community how to observe these non-sidereal targets. So you may think that if you want to take long exposure of an asteroid to get good signal to noise, you expose and just track the asteroid. But the best way to do it would be to take multiple 30, 45-second or 60-second exposures and then shift and stack them eventually. And things like this aren't hard, but it's just getting that communication across with the observers. So where does BH Tom actually fit in, and what is out there now that's similar? Well, in the UK, there's this thing called COBS, which is a Comet Observation Database. And it's a well-established platform. A lot of people are contributing their data to it, and there's nice light curves. But this relies on the community calculating the magnitudes themselves, which clearly can lead to large uncertainties in any of the magnitude measurements. Currently being developed at LCO, also based on Tom Toolkit. There's a project called FOMO, which is the follow-up observations of moving objects. And primarily, this is going to take in the alerts from Rubin and focus on the larger end of telescopes from 2 to 8 meters. But again, the main drawback with this is it relies on people already having won their own telescope time and then bringing that to them. With BH-TOM, it's easily accessible for anyone that has a telescope and wants to contribute data. We also do the calibration and standardization of images, which is, it's incredibly important. It already has this established community of observers with really good quality telescopes, as we've seen this week. And then my favorite thing as well is if you contribute any data, even one data point, you get your name on the paper. So it's like a really good incentive for people to keep providing good quality data if their name's attached to it, but then also contribute future observations and show how their work is actually being used. So as I started my postdoc, 3i Atlas was discovered a couple of months ago. So we thought we could get some good science out of it and also use it as a proof of concept to see if BH-TOM can actually work with solar system objects. So 3i Atlas is the third ever interstellar object discovered. So it was discovered on the 1st of July. Back in 2017, the first interstellar object was discovered, which was Oumuamua. And that was not an alien spaceship or alien craft or anything. It was an asteroid. Then 2 years later, in 2019, the second interstellar object got discovered. So that was Borisov. And that was more comet-like. And I believe it was actually an amateur astronomer in Crimea. And then just in July, this third ever interstellar object was discovered. So these are actually the discovery images from the Atlas Chile unit. And they're taken about an hour apart there. And then also I thought I'd just note here that it's about 10 kilometers across total for this object. So it's a fairly standard size for something typical of like a long period comet. So when this comet was discovered, Łukasz had a lot of LCO time that we made use of, but then we also sent a call out to the community. Can we please get as much observations of this target as possible? So on the left-hand side, at the bottom, you can see all the LCO units. But then we've had a significant contribution from the Turkish observatories, Bologna, as we've seen, Uzo. We've got some data from people in Edinburgh, GoTo. So it's been a really a big community effort to get a lot of good data for this year. And people are also enthusiastic. When the call went out, people wanted to contribute data to this new exciting object. So when 3i Atlas was discovered, it was in the galactic plane, right in the center. So obviously it's going to be a very crowded star field. In total, we've got about 3,000 images over about 70 days from July the 4th to September the 11th, using 13 different observatories. And we watched as 3i Atlas moved out the galactic plane. So as BH-TOM does PSF photometry, it's incredibly useful in a busy star field like this. But typically for comets, we want to use aperture photometry. All the signal from comets is in the coma and in the tail, where the PSF profile would typically cut off at the wings. So we're going to use a combination of both of these photometry methods to get photometry here. So when this was first discovered, we weren't sure if it was actually active or not. So to determine if a comet is active, what we have here is a stacked GRIZ image from the 2-meter Muscat instrument in Hawaii, where 3i Atlas is in the center here. And then all the stars are trailed in the background. And what you do is you measure the flux in concentric circles moving out the way, and you sum up that flux. And then you do the same for about 20 to 50 well-measured stars in the local sky around it. And you take the median profile of both. And what you can say is if there's an excess in flux around our object, you can attribute that to some sort of coma. So you can see that gray profile is the comet, and the blue profile is a star. So there is flux above what you would typically see. So there is a coma there, and it's active. when it gets towards the later images and becomes more and more active as it gets closer to the sun, you can clearly see the coma and actually just the tail there as well, going off to the top right. So PSF photometry is not needed at that point. So that's how we tell if objects are actually active or not. So this is very, very preliminary. There's a lot of data still to add here. But what we have is the BHTOM processed and calibrated light curve of 3i Atlas. So the green, red, and maroon just refer to the GR and I bands. And you can see that this object's increased over 70 days by about 3 magnitudes, which is typical for a long period comet at similar heliocentric distances. We still have a lot of data to add. There's about 600 or 700 data points from Ryuzo, very high cadence, fantastic data. Likewise from the Danish telescope in Chile. And we have a significant amount of observations still to add from the Turkish observatories too. But you can see we've used a lot of the data from talks that were actually given this week. In future, we also want to see how this magnitude evolves as a function of heliocentric distance as well as time, to see how this compares to the other 2 interstellar objects, although we have a sample size of only 3. So just to kind of wrap up here, which I guess leaves time for questions. The future version of BHTOM will allow for solar system target requests. We've seen that there was a willingness from the BHTOM community to actually observe objects, and also an enthusiasm as well. And we observed 3i Atlas as a proof of concept that this can actually work in the future. So thanks very much.
Thank you, Fraser. Let's have a time for questions. Yes, please. Many hands.
Naday Kanatanji. Can you comment on the light curve of the light curve of the comet that you show? So can you get some parameters out of this, or I mean, because I'm not really a comet
Sure.
person, so I'm just curious.
So typically what you want to look at, so later on when I said we want to get magnitude versus heliocentric distance, so like how close it gets to the sun. So typically when comets get closer to the sun, the temperature increases, the energy available for sublimation increases, but then that dust and gas and the amount of coma it has in the sky also increases. So you can tell how active it is. We have some nice data from UZO actually, which is about 400 or 500 data points over one night. So we can start to look at rotational effects. But it's very difficult with very active comets, because to look at the surface, you don't want it coma obscured. You can't tell the rotation of the object if it's obscured by the dust coma. So sometimes it can be quite difficult. But it's doing nothing crazy. It's getting brighter as it gets closer and hotter, essentially. But this is still work in progress.
Okay. And just a quick question on this, just to add. So the amount of data that you got with this light curve, and especially what you said about the UZO observations, so that's okay or enough for
Yeah, so this is a good point. Currently, 3i Atlas is not visible. So it's going into solar conjunction, i.e. it's going to be available, it's going to be visible during the day. So back in when we get to December time, it'll become visible again at night. But the idea is that we're going to try and get a paper out soon on the pre-solar conjunction observations.
Yeah.
Yeah, so Miłosz Płoszyński, Gdańsk University of Technology. I'm wondering, because like there is a lot of possibility, I guess, for example, orbit estimation with a lot of with the telescope network. But the thing you showed with the flux distinction of comets, and I'm wondering if it's possible to automate the whole process, to process in this manner every frame on BHTOM. Is it in the talks? Was it considered, etc., to look for undiscovered comets?
Yeah, so this is like very, very common technique. And for most pipelines that focus on comets and looking for activity, this is all automatic, and it already happens. Yeah, so it's a good point.
Thank you.
You have question.
So a practical question. So some ephemeris would be very well known in the solar system, but this object exemplifies where at the time of the discovery, the ephemeris presumably had some errors, right? And then you have to hand hold the object and update the ephemeris, and the error bars get smaller and smaller and communicate with the observers. And so, you know, okay, this is a very special case and you have to do it in person, but in the future, are you trying to automate all of this or some parts of it? You know, actually a related question. So when for a really well-known ephemeris, that should be easy, right? Like there is a standard software for an observer to just click a non-sidereal object with ephemeris and just go.
Let me see if this works here. So when I was talking about the similar platforms that already exist, so here, for example, the FOMO project is going to look at ribbon alerts. So that's more relevant for them where they don't know what the object is already. They're not really sure. And because we're going to be using, 2 meter, 2.5 meter and below telescopes, the chances are we'll have to look at bright objects from maybe, 13, 12 magnitude down to maybe 17, 18. So it will be objects that are well-known, have well-known orbits and predicted magnitudes as well. But it's good to know your niche and where you fit in as well.
Thank you. Let's have the last question Justus wanted to ask. And
Justus from Vilnius University. But really, you put these images on black hole Tom, yes? Because we have in Moleti Observatory some images of this comet, really, but we did it from another purpose, but really I have images.
You have them ready?
And in that case, it is possible to also to uploading to Tom or just, no, it is our images, not give for other.
Sure. So currently, so I started this postdoc like 2.5, 3 months ago. So this is very much a work in progress. So the way we've been doing it for 3i Atlas is one target. We're not automating anything just now. It's a proof of concept. So it's been done essentially every observation. We're making a brand new target, and it's not the way to do it. In future, it should be a case of you upload your fits, you upload the name of the object, and it's just completely automatic. And it'll link these automatically, and it'll be the same as uploading images for a star, for example, or whatever you want. So in future, it should work, no problem.
so thank you, Fraser, for your presentation. And today we have a last presentation by Carolina Nagata on contribution to exoclocks.
Okay, sorry for that. And she's very stressed. I don't know how to use that. Okay, so I will continue the short poster talk for her. Okay, so what's going on with the exoclock? So first of all, we are using our telescope in Chile to provide the data, provide the observations to the exoclock project. What is exoclock project? Okay, so the exoclock project is actually the satellite project to the ESA aerial mission. This is a space mission for the observations of exoplanets, actually atmospheres of the exoplanets. So the basic thing in this project is to keep up to date the ephemeris of the transits for this exoplanets. So what is the process in daily process, let's say? So first we have to plan the observations. So the students are doing that. So then when they get the observations, they have to check the quality of the data. Then they do the basic photometry, provide the light curve, generate the light curve for the transit. They do the first fitting of the transit of the model using the data, the details of the exoplanet. They get that from the webpage of the on the exoclock. Then when they do that, they create the file that they upload to the database. And then we have the final report, which is done by the pipeline of the exoclock. And when it's published, it's accepted. It's published on the web page. So actually, this is the whole process. And when the data are accepted, it was for sometime every year, but right now probably it's every 2 years. They publish all the ephemerides, up-to-date ephemerides of those exoplanets, and those people who contributed to these observations are involved, are co-authors of this publication. So this is one of the example of the submitted exoplanets. So first we have this light curve from the AIJ, Astro Image J. So this is the first test, first fitting. And then we have the last fitting from the ExoClock project webpage. We have also on the right side, we have image with the information how many observations we already have. Also from the ExoClock, but also from the other observations like TESS or others. Thank you.
Questions for ExoClock project? Microphone, I can.
Did I understand that all the data are taken from a single telescope in Chile?
Yes.
So are there any plans to extend this to be able to reach the discriminated against planets in the northern sky? Or
Could you
do you plan to extend the observations to the northern hemisphere?
If we will get the telescope on the northern hemisphere, yes. That's the plan, actually.
Well, fingers crossed.
Yeah, thanks.
More question?
Oh, sorry. How many planets you've observed already? With
If we checked that lately, I think 200. But in the database, we have 70 maybe.
I don't see any more hands. So let's thank the project again.
So that is it. I need to download the slides first for us. Goodbye. That's weird, no? That's better. Okay, so that's it from the scientific part of this meeting, from the talks part, because we are not done yet. Before we will leave this room today and for this week and for this year, most of you, I guess, let me summarize what is still ahead of us. First of all, today we have a dinner. The dinner starts at 8. It's in the Hotel Nivaria. Some of you are staying there. So first of all, organizational things. Don't forget your badge and don't forget the thingy, the menu thingy, because otherwise you are not eating. You need to bring it, and then please, during the dinner, you need to have that in front of you, because then the waiters will be able to serve what you ordered, right? So if you are not staying in Nivaria is the hotel in La Laguna. Yesterday, when we were coming back from the tour, we stopped there. So if you will go by tram, then this is the final stop in La Laguna. It's called Trinidad, and from there it's about 5 to 7 minute walk. There is a QR code if you want to follow, but it's Hotel Nivaria. You have the name also on the conference website, so we will find out, I guess. The dinner starts at 8, so be there at 8, because we were told that we will not start if we will miss someone. So there will be then 70 angry people waiting for this guy that will come late. So please be on time. Tomorrow, we have the hackathon. You know that this will start at 10, but because of this ID that will be checked, please come to the IC at around 9:30 or between 9:30 and 10. But at 10, if you will arrive at 10, then you will not get in at 10, right? At 10, we start with the plenary. You need to have your name tag, again, this conference one, and the ID you gave us, the ID or passport. So we need, or the guard will ask for the physical thing, right? So you need to have the card or the passport or ID with you that you will show to the guard. We start with the plenary introduction in Ola, which is the biggest room at the IAC headquarters, which is just next to the reception. So you will not miss it on the way to cafeteria. So if you want, you can go for a coffee. You will not miss cafeteria. It's just, straight. But we start at 10 with the introduction, and then we will split. You should have received email from Łukasz in which group you are based on your responses you provided us. So then we will split. We will tell everyone tomorrow which room, which person you will follow, where you will be. So you should have your own laptop because this will be very interactive tomorrow. You should join Slack if you have not yet done so. The link is also in the email that I have sent you with the Zoom link and the Slack link before the conference. And we remind that you can have lunch and coffee at the Institute, which is not a part of the registration fee, so you will need to pay for yourself, but it's possible to do that directly at the Institute. You don't need to go anywhere. We have cafeteria, which is serving lunch from 1, so no lunch in Spain before 1, but you can have a sandwich or anything even if you arrive early. So if you will come at 9, you can have that tomorrow. So once again, I am reminding everyone, this hackathon will not happen here. So if you will be here at 10, this part will be closed and you will not find anyone. It's at the IAC headquarters, which is here again, you have a short description. So it's the tram stop, which is called Museo de la Ciencia. It's 3 tram stops above us. So people coming from Santa Cruz, it's 3 stops more. People coming from the other direction, from La Laguna, it's a bit less travel time. So then the tram stop is called Museo de la Ciencia. And what you see here, then this is the museum. This is the tram stop, right? Then you walk around the museum and the gate is on this street here. So here you will enter behind this museum. You will see the flags and there is a logo and there is a gate with the thing for cars. So there is a booth with the guard that will ask you for your ID, and only after he will register you in the system, you will get another thing that you will need to carry with the visitor pass, and then you will be able to get to the building. So then you will just walk from here and you will enter the building. And then we will take care that someone will help you there. So a few more things. We will be happy if you will provide us the feedback. And given that not everyone is coming tomorrow, I would like to say that today we will provide the link also by email, but especially this local part of us will be happy to know how you liked the organizational part, how you like the venue and the program. Given that I think we agreed that we are asking also about dinner, right? Don't feel that now, please, because you cannot tell us now how you enjoyed your dinner. So it's anonymous. It's just for us to know how you feel about the venue, social program, and so on. I will distribute the link also by email. the final reminder, if you want us to issue the certificate of participation, don't email us. You need to fill this survey. The QR code is also on the table there. So if you will be leaving, you can scan that. Fill that as soon as possible. We will issue the certificate confirming that you were here, that you gave a talk, depending on your needs. And if you gave a talk, if you didn't, then you are not getting that. But please do that through the survey. Any requests by email will be ignored for that, because we have a specific form for that. So I think we had a nice time here, full of exciting things here at the IAC Tech. Tomorrow you will see where we all work, our workplace at the IAC. So this is a conference photo. I think Łukasz already posted that on Slack. It's also on the conference website. So if you want to have a memory and download that and print that in a A0 format to your living room, you can download that from the conference website as well. We also collected a nice set of memories for us in the guest book, which is our banner. So if you have not signed that, please do that. On the way out, the banner is still there. The one thing I would use this picture to is to actually say something about people who are not seen, not only on this picture, but who were not seen for most of the conference, because most of them actually were sitting behind you. And these are my colleagues from the LOC that did a great job during this week. And some of us, like me, and Paul, we all saw, right? But those people there did a great job, and they were not seen. That the job was not seen, not only on that picture. Some were hiding on that picture as well, but also during the week. So I would like to actually thank all of them, because the work was what made this conference a success. And with that, I will now invite Łukasz on the stage, the chair of the organizing committee, to close today's session.
Thank you, Jaro. I don't have much to say. I just wanted to say that the slip of tongue, I said at the very beginning that this is the best meeting, where I wanted to say the largest. So I now agree with both. It was the largest and the best so far. So I wanted to thank you all for coming. Thank you all for contributing to with your talks, with your discussions. And I think it worked pretty well in terms of the program, which was full of different topics. But then we had a lot of time during coffee breaks and lunches where all the discussions were carried out. And I could see lots of connections being made. Not only myself, I made a lot of connections, but also between yourselves. So that's great. That's why we keep doing these meetings, to connect people and to science to thrive. So I joined the thanks to the local organizing committee, because there was so many things happening in the background. It was probably one of the easiest meetings for myself to organize, because everything was sorted out by the local people. So that's great. I thank all the people who gave talks and contributed here. And I have to thank the sponsors, of course, the ACME grant, the University of Warsaw, local funding from the foundation I cannot pronounce, Gaia, whatever. Sorry, Gaia. And everyone for coming here. So we'll keep thanking each other during the conference dinner tonight, and I will see some of you still tomorrow, so please stay with us. And of course, stay in touch, and hopefully I'll see all of you or some of you next year at the 17th workshop. Thank you. Some Mediterranean island I have in mind, so we'll go to an island. Okay, thank you very much.
There is still a bit of food left. So on the way out, you can take it. I know that we have a dinner. The dinner is in 3 hours.
So to keep furthering the connections, if somebody is interested in going for a beer before the dinner, let me know. We can.